the difference?
Okay, I think we're live now, according to John. I also see it on my screen. So I think let's get started without further delay. Okay, welcome everyone. This is the 16th session of our computer architecture course. And today we're going to have hopefully 5 research talks, continuing the cutting edge research directions that we've been exploring. And today's talks will be mainly focused on error mechanisms, reliability, and security, hardware security vulnerabilities. And the first 3 talks are specifically on the RowHammer vulnerability. In the first talk, we have Hassan as the presenter. Hassan is a PhD student in my group, and he's done a lot of work on DRAM in general and RowHammer in particular, as well as latency reduction mechanisms in DRAM. And today he's going to talk about a new methodology for uncovering In-DRAM RowHammer protection mechanisms that are implemented in DDR4 chips. He's going to introduce some more detail in terms of the operational principles of these In-DRAM RowHammer protection mechanisms and describe how to circumvent these protection mechanisms using some custom RowHammer patterns that are developed based on the understanding the methodology provides. And he's going to also discuss some of the implications of these mechanisms in terms of security, like how many more bit flips you can cause, as well as potential defenses. And I must also mention that this Hassan was a co-author on the trespass work, which first showed that the DDR4 chips that are advertised as RowHammer free are actually not RowHammer free. You can actually circumvent them. And this work builds on the trespass works, but essentially enables a much more rigorous methodology that can enable you to circumvent the protection mechanisms much more easily than the past. Hassan, please take over.
Thanks, Onur. So before I start, just a reminder, please feel free to ask questions, interrupt me and ask questions. So we have like more interactive class. So the paper is titled Uncovering In-DRAM RowHammer Protection Mechanisms, a new methodology, custom RowHammer access patterns and implications. This was a paper that was published a month ago at a conference called Micro. Yeah, and let's get started with the summary. So as you may know, RowHammer is a critical vulnerability in DRAM that leads to reliability and security issues. If you don't remember exactly like how this vulnerability like happens and what kind of effects it has, I will cover it in the some future slides. But here, let me tell you about like what DRAM vendors do about it currently. So in pretty much like all DRAM chips, I believe in the market today, they implement an in-DRAM mechanism that is typically referred to as target row refresh, or TRR for short. The problem with TRR is that it is obscure, undocumented, and proprietary, which makes it difficult to study, and therefore we cannot guarantee the security guarantees of these in-DRAM RowHammer mitigation mechanisms. So in this work, our main goal is to answer these 2 questions. Is TRR fully secure? Does it really guarantee the guarantees that does it really provide the guarantees that it is supposed to? And the second question is, how can we validate the security guarantees of these in-DRAM TRR mitigation mechanisms? Okay, so we propose UTR. This is a new methodology that leverages data retention failures in DRAM to uncover the inner workings of TRR and study its security. At a high level, UTR performs 2 steps. First, it profiles the retention time of an arbitrary row, let's say row R. And then UTR finds when the TRR mechanism refreshes this row R based on some access pattern, right, that leads to the refresh of this particular row. And this is like how basically UTR builds an understanding of the underlying TRR mechanism. So using UTR, in this work, we analyzed 15 DDR4 DRAM modules from the 3 major DRAM vendors. Through this analysis, we make several key observations regarding the TRR mechanisms implemented in these modules and craft new custom RowHammer access patterns that evade the TRR mechanisms and cause RowHammer bit flips. So basically, yeah, we show that these TR mechanisms implemented in DRAM today are not really effective, at least not for like all different access patterns that can be executed on the DRAM devices. So our results show that first, all 45 modules we test across 3 vendors are vulnerable to our new RowHammer access patterns. Second, at least our access patterns cause at least 1 bit flip in almost all DRAM rows in many of the modules. And this makes system level attacks easier to mount, as the attacker basically has the ability to cause a bit flip in almost any row inside the DRAM module. Okay. And third, we observe that our access patterns cause up to 7 bit flips in an 8-byte data word. And then this is important because it makes ECC ineffective, and systems equipped with ECC also susceptible to RowHammer attacks. And this is simply because like 8-bit flips, 7-bit flips is much more than what ECC can typically detect or correct. And we believe UTR will facilitate future research by leading to the development of more secure RowHammer protection mechanisms. This is the outline of the talk. I will start with describing some DRAM basics. Here, I show a typical system with a CPU and a DRAM module that has several DRAM chips. Inside each DRAM chip, there are multiple banks, which contain main DRAM cells organized as a 2-dimensional array. DRAM cell stores a single bit of information as electrical charge. And in a bank, the cells are vertically connected to sense amplifiers, which can read the data from the cells and update it if needed. And cells are horizontally organized as DRAM rows. Okay, so now let's look at DRAM commands that the memory controller issues to DRAM in order to basically perform an access. So first, the memory controller activates or opens a row that contains the cells that needs to be accessed. The activate command loads rows data into the sense amplifiers, and this is actually where the data can be accessed, right? So, and yeah, after the row is accessed, the memory controller issues a precharge command, and this precharge command closes the open row, so a new row from the same bank can be activated. And this is basically how DRAM is accessed. Each DRAM cell encodes data in fundamental leaky capacitors, and here's a simplified diagram of a DRAM cell, where the capacitor in red stores the data, and the access transistor is enabling or disabling the access to this capacitor. There are a number of leakage paths which by which charge can enter or exit the capacitor. The important thing to note is that stored data can be corrupted if too much charge leaks, which is the same thing as saying if the capacitor voltage degrades too much. And here's a simplified diagram of the capacitor voltage over time. You see that the voltage decreases over time in an exponential decay. This is when the cell is not accessed for a long time, right? So we don't activate this, the row that corresponds to this cell that we are looking at right now. There's a threshold Vmin under which we can no longer guarantee that we will correctly read the data that was originally stored in the DRAM cell. But as long as cell's voltage remains above this line, here showed as a green region, we can correctly read the data, and we consider this a retention success. However, if the voltage drops below this Vmin threshold, we cannot correctly read the data back, and then we call this a retention failure. In order to prevent retention failures from charge leakage known as retention failure, periodic refresh operations are issued to recharge the capacitor voltage. And the interval between refresh commands are referred to as the refresh window. Okay, so now I will tell you about RowHammer and the main RowHammer protection mechanisms implemented in DRAM chip today, or at least what is known or what is can be intuitively inferred based on the information available online. In order to access data from a DRAM row, say row 2, the memory controller first opens or activates this row, as we saw in the previous slide. So after all requests from this row 2 are serviced, the memory controller must close or precharge the row in order to begin accessing data from another row. Due to increase in cell-to-cell interference as a likely result of increased cell packing density, rapidly activating and precharging the DRAM row can result in bit flips in nearby rows. Continuing to access the same row causes even more failures in nearby rows. And this is basically the phenomenon known as RowHammer. We refer to the rapidly accessed row as the aggressor row, and the rows containing bit flips as victim rows. To protect their DRAM chips against RowHammer, DRAM vendors currently implement RowHammer mitigation mechanisms, typically called target row refresh, or TRR. And the key idea of TRR is to refresh nearby victim rows upon detecting a potential aggressor row. We demonstrate how TRR operates at a high level. The TRR mechanism detects an aggressor row as a result of repeatedly activating and precharging the same row. To protect the neighbor victim rows from experiencing RowHammer bit flips, TRR refreshes the victim rows by performing TRR-induced refresh operations. TRR refreshes victim rows by piggybacking TRR-induced refreshes to the refresh commands that the memory controller periodically issues. So basically what this means is that to make this TRR mechanism work, the memory controller operates exactly as it was operating before without this TRR mechanism. But inside, when performing a refresh operation, the DRAM now is doing more work, basically. In addition to refreshing rows like periodically in fixed order, it is also performing refreshes to these neighbor rows of the potential aggressor rows. Okay. So although this is how TRR operates at a high level, different vendors implement TRR differently, and the exact operation of these TRR mechanisms is unknown. Therefore, TRR is obscure, undocumented, and proprietary. And because of this, today we cannot easily set the security properties of TRR and make sure it is fully secure. And our goal in this work is to study in-DRAM TRR mechanisms to understand how they operate, assess their security, and secure DRAM completely against RowHammer. And I will now present in more detail the methodology that we use to uncover these internal TRR operations. We propose UTR, a new methodology to uncover the inner workings of TRR. And the key idea of UTR is to use data retention failures in DRAM as a side channel to detect when a certain row is refreshed by TRR. UTR consists of two main components that we call row scout and TRR analyzer. Row scout finds a set of DRAM rows that meet certain requirements as needed by the TRR analyzer and identifies data retention times of these rows. TRR analyzer, on the other hand, uses the rows that row scout provides to distinguish between TRR-induced and regular refreshes and builds an understanding of the underlying TRR mechanism. Okay, let me describe the two components in more detail. So the goal of row scout is to identify a list of DRAM rows which must be useful for TRR analyzer. And basically, row scout finds such rows and profiles their retention times. Row scout must find rows with consistent retention times. This is critical for UTR to correctly infer whether or not a row has been refreshed by a TRR-induced refresh operation. Row scout must find DRAM rows whose retention times do not change over time due to variable retention time or VRT effects. Row scout must also find multiple rows, or what we call a row group, that are located at certain configurable distances and have the same retention time. And this is important and required so UTR can observe whether or not the TRR mechanism can refresh multiple potential victim rows at the same time. I will now explain the row scout operation using a flowchart. First, row scout searches for DRAM rows that have retention time T. Row scout profiles the retention time of a DRAM row by simply initializing a row with known data pattern, such as all ones, and measuring for how long the row correctly retains its data without being refreshed for the time interval T. Step 1 outputs addresses of rows with retention time T, which is initially set to a small value, for example, 100 milliseconds, with the aim to minimize how long UTR experiments take. This is because the time that UTR experiments take largely depends on the retention times of the rows that row scout finds. So second, row scout puts together rows that have certain retention row addresses, certain row address distances among them, as indicated by the configuration parameter that we call row group layout. And this is an example of a row group layout that has 3 rows indicated by V that are 1 row address apart. Depending on how many rows are found in step 1 and how many of them can be combined to match this row group layout, step 2 outputs a set of candidate row groups. Next, if the candidate row groups are fewer than needed, RowScout increases T by a certain amount and returns to step 1 to basically find more rows. If the candidate row groups are enough, RowScout repeatedly profiles the retention time of the rows in the candidate row groups for many iterations. This is to verify that all rows in a row group have consistent retention times and do not experience variable retention time effects. Candidate row groups that have consistent retention times are output as row groups, and the rest of the candidate row groups are discarded. If the number of retention time verified rows is not enough, RowScout again returns to step 1 to search for more rows with increased retention time T. And these steps repeat, as I explained, until RowScout finds a sufficient number of row groups, and finally RowScout outputs a list of retention time profiled rows to be used by the TR analyzer. I will now describe the operation of, yes, there's a question.
I'm not sure I got step 4 very well.
Step 4. Yeah, so let's say you measure the retention time of a certain row, let's say row at address 100 of bank 0, right? So you find that it can retain its data correctly for 100 milliseconds. You repeat the exact same experiment again. Nothing changed in the your experimental setup. But this time you find that it retains data for longer, for 200 milliseconds. And this can happen due to various reasons. One reason is what people refer to as VRT, or variable retention time. So due to not exactly known reasons, a cell may change basically its capability to retain data over time. So usually there are 2 modes for each cell. The cell is either in low leakage mode or high leakage mode. And usually it has 2 different retention times, either let's say as in the example 100 milliseconds or 200 milliseconds. And it is basically transitioning between these 2 modes over time due to some random or random-like effects. And basically we do this step 4 repeatedly 1,000 times or more to ensure that this cell is not experiencing such issues. So we only work with cells that are guaranteed to be guaranteed to have the same retention time over a long period.
So then what do you do in step 1?
So step 1 is just a step to initially find what to work to find some candidate rows to work with. So if you start with a random row and then put it into this step 4 directly, that won't be efficient because the row may have a very low, very large retention time, right? So we don't want to work with rows that can retain data for minutes. Then it will make the experiment very slow. It is possible to use such rows, but it is not efficient time-wise. Yeah, so this is why we start with a very small t and first try to filter out rows that have very low retention times and try to use those if possible. Okay. And now let's move on to the second step. In the second step, we will look at the second component, TR analyzer. And the goal of this component is to use RowScout provided rows to determine when TR refreshes a victim row. So at a high level, TR operates in 3 steps. It runs a certain DRAM access pattern, or we can call it a RowHammer attack. Second, TR analyzer monitors the retention failures that RowScout provided rows experience to determine when TR refreshes any of these rows. And third, based on when and which of the RowScout provided rows are refreshed by TR, the user develops an understanding of the underlying TR operation. And so here we basically, in step 1, run some access patterns that we expect to affect the TR mechanism to target potentially these rows that are being monitored, rows that we know their retention times, right? And basically, if the TR mechanism refreshes these rows, we expect to see no failures after the retention time that we have measured. But if there are still bit flips, that basically means that the TR mechanism did not target these rows and it did not refresh these rows. And this is basically by picking different like types of access patterns by hammering different aggressor rows, we can identify which rows, hammering which rows how many times is causing these like retention profile rows to be refreshed. And okay, so here's a like more pictorial view of the same thing that I've just described. As a first step, TR analyzer initializes the retention profile rows with known data. In this step, TR analyzer also initializes the aggressor rows that the user specifies to like hammer. And then this is because of data dependency effect of the RowHammer, right? So like depending on what data you have in the aggressor rows, you may or may not be able to cause bit flips in the neighbor rows. So it is important to like work with known data in the aggressor rows as well, in addition to the victim rows. Okay, so the user specifies aggressor rows in locations relative to the retention profile rows, as you see in the row group representation over here, example over here. And yeah, if you assume like a row group as shown in here with 3 victim rows, 1 row apart, a user may specify an aggressor row, a single aggressor row, to be between the first 2 victim rows. And in that case, we expect to this aggressor row to affect the 2 victim rows as shown here, right? And then we also expect the TR mechanism to refresh 1 or both of these victim rows. But the user can also specify 2 aggressor rows. Okay, so when I forgot to say, so we usually refer to this as single-sided RowHammer when there's a 1 aggressor row to hammer 2 neighbor rows. But it is also possible to use 2 aggressor rows like this, where like the row in the middle is being hammered by both of the aggressor rows at the same time. And this basically disturbs the middle victim row more than the 2 victim rows at the sides, but they're all disturbed by some level. So like the TR mechanism may potentially want to refresh all of these victim rows shown in here. Okay. Second, a TR analyzer performs a set of operations to reset the internal state of the TR mechanism so that it isolates the experiment about to be run from prior experiments that could have potential changed TR mechanism state. This step is optional, and we provide more details in the paper on why this step is sometimes needed and how we reset TR's internal state. Yeah, so basically here, this is important, especially if it is suspected that the TR mechanism is stateful, right? So it is keeping some sort of a history and takes actions depending on what has been the access pattern in the past or in the previous experiment. So in order to like get to the same state on like every iteration of an experiment, we would like to reset this TR's internal state so we can isolate prior experiments, right? So we can like relate the observations only to the access patterns that we perform in this particular experiment. So here, what we expect after time t, after initializing these rows is, if the TR analyzer does not activate any of the victim rows for their profiled retention time t, we expect to see bit flips due to retention failures in these rows once we read their data back, as I said, after time t. In order to make TR perform a TR-induced refresh operation or target these like neighbor victim rows, the DRAM has to receive a refresh command. So this is why I explained in the previous slide, right? So like the DRAM can perform these TR operations, these like targeted refreshes within the time allowed to perform the refresh operations, the regular refresh operations. So the TR analyzer issues a refresh command when the victim rows are not refreshed for half of t. And this is to ensure that a victim row retains data correctly until it is potentially refreshed by a TR-induced refresh. And similarly, it correctly retains its data after a TR-induced refresh until TR analyzer reads rows data. Okay, so like if there's a retention failure at the point where a refresh is issued, even if TR refreshes that victim rows, since it already has a bit flips, it has no chance to correct that bit flip, right? So that experiment won't be useful. And for that reason, it is very important to issue those refreshes at the middle point or at some point where we know that no retention failures will happen. And then we know that by just like carefully profiling these rows and knowing like the minimum retention their retention time and use T basically to be equal to their retention time, not much larger than that. Okay. In order to make TR perform, in order to make the TR mechanism target these victim rows that we know their retention times, the user may activate many times or hammer aggressor rows near these victim rows. And this is like when in this experiment, aggressor hammers happen, right? So like right before the refreshes. And this is again important because like if we perform the hammers later after the refresh, that doesn't make sense since the TR mechanism basically is not suspecting an attack. So it has no reason to refresh these victim rows. So we give it that reason basically. And here, this is the control experiment, right? So like we can decide exactly which aggressor row to hammer how many times, and then repeat the experiment with different hammer counts and the different orders of these hammers to check when the TR mechanism targets the victim rows and when it does not. In addition to aggressor rows, the user can also specify dummy rows. These are pretty similar to aggressor rows, like in terms of operation, but the only difference is that dummy rows are selected from some different region in the same bank, like far from the victim rows. And the purpose of these dummy rows can be just simply trying to like trick the TR mechanism to target something else instead of the actual victim rows that we care about, right? So like this is important to important when we try to understand the TR mechanism and try to develop an access pattern or an attack that bypasses the TR mechanism. So here are some configuration parameters that the current tool that we implemented provides. And this enables studying like different parameters, perform different experiments to like analyze the TR mechanism in depth. Overall, the TR analyzer user, the user of the TR analyzer tool understands how a certain TR mechanism operates based on when the TR mechanism refreshes which of the retention profile rows. Yes.
So if you're going into it later, please, I'm happy to wait. But I was wondering, I guess we have to disable refreshes to see retention failures in the first place, right? But then we have to issue refreshes to see TRR in action at all. How do we know that the refresh that it wasn't the original refresh command that refreshed the row and not TRR?
Yeah. So regular refreshes are periodic. They do not happen too much, and they are very easy to distinguish from the other refreshes. So first, like when there's like a RowHammer attack and the TR mechanism refreshes these victim rows, this happens very often, right? So like for every refresh, like every iteration of this experiment where we do only one refresh, it is basically very likely that one of these victim rows will be targeted. And like 99% of the times, this will be due to a TRR. Or why did I say that? Simply because like one refresh command is refreshing only a very few rows from each bank, right? In order to refresh the same row again by like regular refresh, the memory controller has to issue about 8K refresh commands in total. So only 1 out of 8K refresh commands will target the same row for TR for like regular refresh. And yeah, to be 100% accurate about like that, like about distinguishing TR refreshes from regular refreshes, we can simply run an experiment where we don't do any hammers, right? We do only one refresh, and then repeat this for like thousands of times, right? To issue like thousands of refresh commands. We will see a period at which the same row is refreshed and it does not contain any retention failures. And this way we can find exactly like which refresh commands are refreshing this row. And this is basically what we do. Was it clear? I think I took a very complicated approach to explain it, but okay. Okay, yeah, basically, yeah, these are periodic, and when they happen, yeah, it is very easy to tell. Okay, I guess no other questions. So I'll now describe the observations that we made by analyzing existing TR mechanisms using UTR and explain the new RowHammer access patterns we crafted. Okay, so maybe, yeah, okay. So to implement UTR and conduct the DRAM experiments, we use SoftMC, which is an FPGA-based DRAM testing infrastructure. We modified SoftMC to support DDR4 modules. We use SoftMC because it provides fine-grained control over DRAM commands, timing parameters, and temperature. So by using this FPGA infrastructure, we basically get full control over what commands are sent to the DRAM, right? So we can disable or enable periodic refresh commands. Here in these experiments, it is disabled, and we issue refresh only at like exact times when we want it to be issued, right? So like this, we basically using this tool like is helping us a lot in terms of like convenience to conduct those experiments. Like compared to a CPU system where you can access the memory using like load store instructions, things are much easier, right? By having this like precise control. Okay, so in this study we analyzed 15 DDR4 DRAM modules from each of the 3 vendors. And yeah, in the paper we have a table that basically summarizes our observations. So I won't like look into this table into too much detail for now, but maybe later we can come back to this if there are like questions. But basically this table is showing like what different characteristics each module have. For example, it shows the HC first value for each of the modules, and HC first is like minimum hammer count required to cause a bit flip. Or it shows like what patterns are well, it's not showing the patterns directly, but it is showing basically some observations regarding like what the TR mechanism implemented in each of these modules look like. Okay, yeah, I will cover the key observations anyway, so I won't keep talking about that table anymore. Okay, so let's look one by one at the key observations we make regarding each vendor's TR implementation. So in this talk, I will omit the details about how we use UTR to make these observations. But these are in the paper, on the paper. And also I will talk about one particular TR mechanism from each vendor, but we found small differences in the TR mechanisms of modules manufactured at different times by the same vendor. Okay, so let's start with vendor A. Sorry, vendor A performs 3 types of refresh operations. It performs regular refresh that every DDR4 DRAM does. And in addition, it performs 2 TR-capable refresh operations, which we refer to as TRF1 and TRF2 here. In this timeline, each tick represents a refresh command that the memory controller periodically issues. During the first 8 refresh commands, the DRAM chip performs regular refresh only. On the 9th refresh command, the TR mechanism performs TR-capable refresh TRF1. And during the next refresh commands, the DRAM chip again performs regular refresh, and these are followed by a TRF2. So overall, the TR mechanism uses every 9th refresh command to perform either TRF1 and TRF2 in interleaved manner. So what is the difference between TRF1 and TRF2? We suspect that vendor A's TR implements a counter table to keep track of repeatedly activated potential aggressor rows. The table has 16 entries, where each entry contains a row address and a counter value to indicate the accumulated hammer count of the corresponding row. When performing TRF1, the TR mechanism refreshes the neighbor rows of the row ID that corresponds to the largest value in the table. On the other hand, TRF2 uses a pointer that indicates the row ID from the table to refresh its neighbors. After performing one TRF2 operation, the TRF2 pointer advances to the next entry in the table in circular manner. So it basically looks like it looks very similar to how periodic refresh happens, right? So like we iterate over every row in DRAM one by one, and here it is iterating over this table and selecting one aggressor row to refresh its neighbors. Okay, so this was like vendor A, and then okay, so how can we circumvent this TR mechanism? Our approach in crafting a RowHammer access pattern is to aim for having the attacked aggressor row discarded from the counter table prior to a DRAM refresh command. And with this, our goal is to let TRF1 and TRF2 pick any other row from the counter table, but not the aggressor row that we actually hammer. To this end, we craft the following access pattern. Immediately after a refresh command, we hammer 2 rows, A1 and A2, that are 1 row apart to perform double-sided RowHammer attack. And we hammer each row n times. Then to discard A1 and A2 from the counter table, we hammer 16 different dummy rows, n plus 1 times each. So recall that the table size was 16 entries, right? This is why we use 16 different dummy rows here. By hammering the dummy rows more than the aggressor rows, we make the TR replace A1 and A2 in the counter table with the dummy rows. The maximum value of n depends on how many hammers can be performed during the time interval between two refresh commands. So when we refresh at default refresh rate, 64 milliseconds, there's like a specific timing between two DRAM refresh commands. And basically, depending on how large that is, we can perform a limited number of activation commands. Okay, so by like performing this access pattern, we prevent the TR mechanism from detecting the aggressor rows, since both TRF1 and TRF2 can detect a row from the counter table, which now contains only dummy rows. To execute this RowHammer access pattern, it's important to synchronize the accesses with the refresh commands to perform aggressor and dummy row hammers at the right time. And we conclude that one can circumvent vendor A's TR mechanism by discarding the actual aggressor rows from the counter table by sufficiently hammering a set of dummy rows. Okay, let's look at vendor B. Different from vendor A, here we observe a single type of TR-capable refresh. We observe that there's a TR-capable refresh on every fourth refresh command that the memory controller issues. We make two observations. First, TR probabilistically samples the address of an activated row as a potential aggressor row. And second, the newly sampled row overrides the previously sampled one, even if the neighbors of the previously sampled row were not refreshed by the TR-induced refresh rate. So these are the two most relevant observations, but we have more in the paper. And basically, TR-capable refresh command targets the row address that has been last sampled by the TR mechanism. And yeah, this is like how the TR mechanism of vendor B operates. And it seems that this mechanism assumes that an aggressor row will be activated frequently enough such that the TR will sample the aggressor row with high probability, even if the probability of a single row activation being sampled is low. Okay, to circumvent the TR mechanism of vendor B, our approach is to maximize the probability of having a sampled dummy row, hammering the dummy row as many times possible before a subsequent TR-capable refresh. So basically, after a TR-capable refresh command, we initially hammer the actual aggressor rows that we want to hammer. Again, A1 and A2. And after those, we hammer in the remaining time before the next TR-capable refresh, we hammer dummy row. It is sufficient to hammer only one dummy row, and we hammer it as much as possible. And here the hope is that it will be sampled and override one of the two rows that we previously hammered, A1 and A2, such that the next TR-capable refresh command will target the dummy row instead of the actual aggressor rows. So in conclusion, one can circumvent the B TR by overwriting a sampled aggressor row by making the TR mechanism sample a dummy row prior to a TR-capable refresh command. Let me also quickly go over vendor C. Vendor C also uses one type of TR-capable refresh, and this time every 17th refresh command is TR-capable. So here the ratio of TR-capable refreshes is much lower. Based on our analysis, we suspect that this TR mechanism is more sophisticated compared to the other two vendors. It potentially uses a combination of both counter-based and sampler-based approaches. And we make two key observations that help us craft an effective RowHammer access pattern. First, we observe that TR detects a row across only the first 2K activations following a TR-capable refresh command. Row activations performed after the first 2K activations are basically ignored. The TR mechanism is not like taking them into account when deciding which rows to refresh. We also observe that the rows activated earlier within the 2K activation commands are more likely to be detected by TR. So very first rows activated within these 2K activation commands are the most likely targets of the TR mechanism. Basically, TR probabilistically detects an aggressor row within the first 2K activations while favoring the earlier activations more. To circumvent the TR mechanism of vendor B, our approach is to first activate dummy rows to maximize the probability of making TR detect the dummy row instead of the aggressor rows that we will hammer later. So this is sort of like the opposite we do, what we do with vendor B. Yeah, and after a TR-capable refresh, we first hammer a dummy row And then we hammer two aggressor rows A1 and A2 until the next TR capable refresh. The aggressor rows are less likely to be detected than the dummy rows, especially when we first perform a large number of dummy hammers. In conclusion, one can circumvent vendors CTR by first hammering dummy rows to make the actual aggressor rows less likely to be detected by TR. Okay, I guess no questions. So I will present the RowHammer bit flips that our new access patterns cause. So leveraging the understanding we developed using UTR, we craft new RowHammer access patterns that circumvent the TR mechanisms of the three major the DRAM vendors. We evaluate the effectiveness of these patterns on 45 DDR4 DRAM modules, and we find that the new RowHammer access patterns cause a large number of RowHammer bit flips. Let's look at the effectiveness of our new RowHammer access patterns at DRAM row granularity. This plot shows for each of the 45 modules we test the fraction of rows that experience at least one RowHammer bit flip compared to all rows in a DRAM bank. First, we find that all 45 modules we tested are vulnerable to our new RowHammer access patterns. Further, in 20 of the modules, our RowHammer access patterns cause bit flips in almost all of the rows. But why are some modules less vulnerable? You find that it is because of three main reasons. First, some modules are fundamentally less vulnerable to RowHammer in the sense that the rows in those modules can tolerate a higher number of hammers before experiencing RowHammer bit flips. Second, some modules implement a different TR mechanism that our custom access patterns are not as effective. We believe understanding those different TR mechanisms can help us crafting more effective RowHammer access patterns. And third, some modules of vendor C implement a unique row organization that appears to mitigate RowHammer at DRAM circuit level. We conclude that although some modules are less vulnerable, our access patterns successfully circumvent the TR implementations of all three DRAM major vendors. The new RowHammer access patterns cause a lot of RowHammer bit flips, but can conventional DRAM ECC protect against those bit flips? This is a simplified diagram of a DRAM module with ECC. In this example, in addition to 4 DRAM chips that store data, a 5th DRAM chip stores redundant ECC data. Each chip provides 16 bits or 2 bytes of data per cycle. A 2-byte data chunk is called a symbol, and all data symbols constitute a 8-byte data word, and all symbols, including the ECC symbols, constitute a 10-byte coder word. The memory controller uses its ECC engine to decode incoming coder words. When there are bit flips in the coder word, the conventional DRAM ECC can correct a single bit, or it can be designed to correct a single symbol. The ECC engine can detect 2-bit errors or 2 symbol errors, and the ECC engine cannot correct or detect 3 or more bits or symbol errors. Now let's analyze the RowHammer bit flips at a smaller granularity and see whether ECC can protect against RowHammer bit flips that our access patterns cause. So this plot shows individual for each DRAM vendor the distribution of 8-byte data chunks that have 1 to 7 RowHammer bit flips, and the y-axis is in log scale. The majority of the 8-byte data chunks are those that have only a single RowHammer bit flip, which can be corrected using typical single error correction ECC. However, our RowHammer access patterns can cause at least 3 bit flips in modules of all 3 vendors. Further, we see up to 7 bit flips in many data words, which the segment ECC cannot correct or detect. And we conclude that conventional DRAM ECC cannot protect against our RowHammer access patterns. In the paper, we have more observations regarding how the TR mechanisms of the 3 vendors operate, a detailed description of the RowHammer access patterns we crafted, a sensitivity study on how the number of RowHammer bit flips change when we sweep the number of hammers per aggressor row, and observations and results for individual DRAM modules. And here's the table that I showed previously too. So let me quickly conclude my talk. The RowHammer vulnerability of modern DRAM is a critical, reliability, and security threat. And the security guarantees of the TR, which is the commonly used RowHammer protection mechanism today, cannot be easily studied because the details are obscure, undocumented, and proprietary. And in this work, our main goal is to answer these 2 questions. And for that, we propose and develop UTR, a new methodology that leverages data retention failures in DRAM to uncover the inner workings of TR. Using UTR, we analyze 15 DDR4 DRAM modules from each of the 3 DRAM vendors. And through these analyses, we make observations that help us craft new RowHammer access patterns that cause bit flips in all the modules that we have tested. And many of these modules we find to have bit flips in almost all of their rows. And we also find that our access patterns can cause up to 7 RowHammer bit loops in a single data word that makes ECC ineffective. So we conclude that TR does not provide security against RowHammer and can be easily circumvented using the new understanding provided by UTR. We believe and hope that UTR will facilitate future research by enabling rigorous and open analysis of RowHammer mitigation mechanisms, leading to the development of both new RowHammer attacks and more secure RowHammer protection mechanisms. Okay, and yeah, this was the end of this first part. Are there any more questions?
Yeah, so it seems that for the 3-access pattern, it requires synchronization with the TRR refresh. So I wonder from the attacker's perspective, how easily or how hard it can be done. Or if I just don't know when those commands are issued and I just do it randomly, then what is the chance that I can hammer that DRAM?
Yeah. So yeah, one option is definitely to do it randomly, right? So maybe not completely randomly, but you know that a row will be refreshed every 64 milliseconds or 32 milliseconds, whatever. So you can basically perform your attack in different times within this 32 millisecond window. So this is one approach. Another approach is actually synchronizing with the refresh commands that refresh the particular row that you're attacking is not that difficult. And we do not discuss that in our paper in detail, but prior work shows that. And basically the approach is to measure the time to access that row. So basically if you issue a request, if you try to read from a row that is being refreshed, you will get your response or you will get your data later than usual. So you'll basically have a higher latency to a row that is being refreshed. And this is basically by analyzing this timing side channel, you can figure out exactly like when a row is being refreshed. And since those refreshes are periodic, they're like happening deterministically, right? So like they repeat at every 32 or like 64 milliseconds. So once you catch that refresh, you can probably like keep synchronized to it by just like measuring the time.
That makes sense.
Mm-hmm.
I think there's one question on Zoom. Can you please ask?
Oh, yeah. The question is, I'm out of curiosity, did you receive any blowback for this research? Because it seems sort of like there's probably a large cost associated with a perfect RowHammer prevention mechanism. And so it seems like the DRAM manufacturers made these imperfect mechanisms knowing they were imperfect, and then sort of like we're hoping to use like by their obscurity sort of to like stall any kind of attack. And so by publishing this research and then maybe providing access patterns, it seems like those like you guys have made it sort of like a more easy fruit for people to go and then go around all of these prevention mechanisms. So yeah, did anybody like I'm curious, did anybody like reach out to you or like was there any lawsuits or anything?
I don't think so, or not yet. But this is not the first work to show that the TR mechanisms are not effective, right? So like the trespass paper showed that before. Yeah, and like that is basically known pretty much like at the time you like published this paper, that was known that these TR mechanisms are not like completely secure, but like we showed basically like exactly why and like how you can bypass those TR mechanisms in a like more efficient and more effective way.
Okay. I guess are you worried that this might be used towards like bad ends, or like is the main hope that by understanding in more granularity the mechanisms by which I guess their systems fail, the DRAM manufacturers can then go and improve what they're doing.
So what is the question exactly?
Oh yeah, sorry, I think that was a bit unclear. I was just asking like whether I guess it's more of a rhetorical question. I just thought like perhaps then like the assumption is that the pros outweigh the cons, right? The cons are that people can now have a lower hanging fruit to unleash more powerful attacks. That's a con, but the pro is that now manufacturers know in more detail the mechanisms by which their TRR is vulnerable. so they can now go and also improve their systems. So I guess it's just a rhetorical question that you guys are, I guess, believe that the improvements to the DRAM will outweigh the cons coming from people who will exploit the existing systems.
Well, okay, so maybe I understand what you said, but the manufacturers should know what mechanisms they implement, right? So like, yeah, I think I agree that they should know that their mechanisms are not perfect already, but maybe having this work out will motivate them more to implement something more effective to like protect against RowHammer. And yeah, I guess you're right. So like somebody can potentially take advantage of our work to perform a more powerful attack. Yeah, but as I said, I think it was also like possible in the past. So I don't think like you can be entirely responsible for that.
Okay,
Yeah.
thank you.
Yeah, I mean, without delaying things too much, I think I definitely agree with Hassan. And in general, that's true for security research that figures out vulnerabilities, right? This is the white hat kind of security research. You basically figure out the vulnerabilities, show the vulnerabilities, and hope that people will improve. It's better that these are known than these are not known, and somebody else is maybe exploiting them without anyone knowing, right? So yeah, it's good to keep things in context. I think these are some good policy related questions, but if you really want to be fundamentally secure, you cannot rely on security by obscurity. And what UTR work clearly provides, building on trespass, is that you can do whatever you want inside your chip, and you may assume that things are working fine, but maybe you're really underestimating smart people out there who can actually figure out what's going on underneath. And maybe you shouldn't be doing that, right? Meaning that you should not be assuming, you should be creating a fundamentally secure solution as opposed to banking on someone else being, let's say, not good enough, or maybe thinking that you are much better than anyone else, right? And nobody will figure out what's going on inside, right? Especially in a protocol like this. So hopefully that made sense, but that's true, I think, in general of security research. And one can take the position that, okay, we're not going to expose anything. But then that's not a good position, because there are smart people out there with not so good intentions as researchers like us, right? They may actually be doing this already and nobody's knowing it. And security by obscurity is seemingly potentially working, but it doesn't look, it may not be really working.
Okay, I think that makes sense. It's just like I was thinking, like, I guess my point was that, yes, but there were also people who are not so well equipped out there, right? People who cannot be bothered. But now maybe with the white hat research, they now have low-hanging fruit by which these people who don't have the talent or the resources, but do have the negative intentions, can now go and do their evil deeds. I guess the point is, like but I guess like this kind of research sort of changes the mentality of the companies, and it also prevents sort of like the worst case scenario attacks where everybody thinks it's secure and there's something out of the blue. Like
Exactly.
Like, you know, you're right. So okay, that makes sense. Thank you.
Exactly, sure. Okay, are there other questions for Hassan?
Yes.
So this isn't really the topic of the talk, but I was wondering about how predictable are these bit flips that you're inducing? Do you have any information about where they're going to happen? Can you know this in advance, or is there some randomness to it?
Yeah, so those bit flips appear to be random, but if you have the chance to profile them in advance, you can know exactly like when they will happen. So basically they're repeatable, but they appear to be like random across devices and like different locations within the same device.
Okay, but so in one row, they're repeatable. Right?
Yes. Okay, I guess then it is the time to continue with the next presentation.
Okay, yes. Thanks, Hassan.
Mhm.
I think we're context switching to another related talk on RowHammer, and Giray will present a concurrent work that appeared at Micro on building a deeper understanding of RowHammer, which basically analyzes the vulnerability of RowHammer bit flips to temperature, to aggressor row activation time, as well as to spatial variation in devices, basically the victim cell's location in different devices. And basically there are new observations that are provided in this work that can lead to both better attacks and better defenses. So this builds a deeper understanding of RowHammer. And these two works, I wanted to put them together consecutively because the first work clearly looks at existing devices and existing protection mechanisms and tries to figure out what's going on underneath and tries to build an understanding of what the existing state of the art in the protection mechanisms from the DRAM manufacturer's perspective are, and shows that they're not very effective. But this work basically looks at the fundamental circuit level vulnerability of RowHammer, and it doesn't consider any of those protection mechanisms. It really looks at the device level issues, like what is the fundamental effect of temperature, for example, on RowHammer. And both types of works actually are really important to develop both better attacks and defenses. And the goal of developing attacks is always to solve the problem, right? So in the end, our goal is to really develop better defenses, but developing attacks actually can enable that goal. Okay, with that, I think, Giray, you can take over.
Okay, thank you, Onur. As Onur said, this is an experimental characterization work called A Deeper Look into RowHammer Sensitivities. Okay, so this presentation starts with some background, actually, but I'm just gonna skip it quickly because Hasan already talked about this DRAM organization stuff and the RowHammer as well. So I guess I don't need to repeat it now. And yeah, you know, this is RowHammer. Okay, let me start with a quick executive summary. So the main motivation of this work is as the density is increasing in DRAM chips, they become more vulnerable to RowHammer in the circuit level, even though there are some security precautions that are taken. But as Hasan discussed earlier, they can also be defeated. So general motivation is that these chips are becoming more vulnerable. And understanding RowHammer is essential for finding solutions. And our main goal is here, like, find effective and efficient solutions, right? And for this, we need a rigorous study that demonstrates how this RowHammer vulnerability varies under different conditions. This is mainly for understanding RowHammer better and developing a deeper understanding into it. And our goal in this work is to provide insights into three fundamental properties of RowHammer that can be leveraged to design more effective attacks and more efficient and effective defenses. In this work, we look at like three different properties. One is DRAM chip temperature. Second is the time that an aggressor row stays active during a RowHammer attack. And the third one is the victim DRAM cell's physical location. And we conduct this experimental study using 272 DRAM chips from 4 major manufacturers. These include DDR3 and DDR4 DRAM chips. And we provide 6 key takeaways and 16 novel observations in the paper. I'm not going to go over all of them, but you can find everything in the paper very clearly. I'll just highlight a part of it here in the summary. This is one of the main takeaways. A RowHammer bit flip is more likely to occur in a bounded range of temperature if the aggressor row is active for a longer time and in certain physical regions of the DRAM module under attack. And our novel observations in this work can inspire and aid future work. for crafting more effective attacks and designing more effective and efficient solutions. So this is the outline of the talk, and I'll quickly start with motivation and goal. So as I said, RowHammer is a DRAM reliability and security problem that gets worse, and denser DRAM chips are significantly more vulnerable to RowHammer. So when we look at some data from the prior work, the minimum activation count to observe a bit flip has reduced by more than an order of magnitude in less than a decade. So in the bottom, you see like the hammer count that is necessary to induce bit flips published in 2014 ISCA paper. And up there, you see another number from 2020. And there's a significant difference in between. And if you look at Trespass paper or other recent papers as well, you will see absolute hammer counts that are around like 15K or 10K, around that region. And even with that shows that even with the on-die mitigation mechanisms, defenses, you can now induce RowHammer bit flips in much fewer hammer counts. And prior research also shows that as this minimum hammer count necessary gets lower, the defenses published in the literature become prohibitively expensive. And we definitely need a deeper understanding of RowHammer to address this problem. And unfortunately, no rigorous experimental study on fundamental properties of RowHammer is out there. So the takeaway is it's critical to gain insights into RowHammer and its fundamental properties. And that's exactly our goal in this paper. So we look at like three aspects, as I said earlier: temperature, aggressive reactive time, and victim DRAM cells physical location to find effective and efficient attacks and defenses. Okay, this is our experimental methodology. It's very similar to UTRR's setup, actually. So here we have a FPGA-based experimental setup where we again use a modified version of SoftMC. We connect a heater module around DRAM, and we control the temperature using a PID-based temperature controller. And this infrastructure provides us with the fine-grained control over DRAM commands, timing parameters, and temperature. So in our methodology, we characterize our DRAM chips at worst-case conditions. And to do that, we first prevent sources of interference during core test loop, which is so we enable this in like several items. So first is no DRAM refresh. So we disable DRAM refresh completely, so that we avoid a victim row getting refreshed during a RowHammer attack. So in essence, we actually disable whatever on-die TRR mechanism implemented in the chip. And we disable DRAM calibration events so that we have precise timing in our DRAM commands. And yeah, as I said, there's no RowHammer mitigation mechanisms. And our tests complete in less than a refresh window to avoid any retention bit flips getting into our data. And we use the worst case access sequence, which is named as a double-sided attack, where we repeatedly access the two physically adjacent rows of a victim row as fast as possible. And this is a list of the DIMMs or DRAM chips that we use. So we use 272 DRAM chips in total from 4 major manufacturers, and that implement 2 DRAM standards and implementing different densities, data regions, and chip organizations. So there are definitely more details about this DRAM chips in the paper. And if you look at the version in Professor Mutlu's website, you can also see the exact DRAM models and like the real names of the manufacturers. So the first analysis is about temperature. So in this analysis, we provide 2 key takeaway lessons. First, To ensure that the DRAM cell is not vulnerable to RowHammer, we must characterize the cell at all operating temperatures. And the second one is RowHammer vulnerability tends to worsen as DRAM temperature increases. However, individual DRAM rows can behave differently than the dominant trend. And we analyze the temperature levels. A DRAM cell is vulnerable to RowHammer. Here, we observe that there exists a lower and an upper bound of temperature, and a DRAM cell experiences bit flips only within this bounded range. But we do not observe any bit flips out of this bounded range. And we call this bounded range as vulnerable temperature range. And yeah, so this table demonstrates the fraction of DRAM cells that experience bit flips at all temperature levels within their vulnerable temperature range. And we observe that more than 98% of vulnerable cells across all chips that we test exhibit this behavior that they experience bit flips in a continuous temperature range. So yeah, they experience bit flip at every single temperature point within their vulnerable temperature range, and we conclude that it's a continuous temperature range. And here we have a population density plot of DRAM cells. These DRAM cells are clustered based on their vulnerable temperature range characteristics. So the x-axis shows us the lower bound of the temperature, and y-axis is the upper bound. And the percentages and the colors in this plot show us the fraction of vulnerable DRAM cells that fall into that particular region. So for example, the annotated place, so we see that 0.4% of the DRAM cells are vulnerable to RowHammer only between 55 and 60 degrees Celsius. And similarly, only 0.5% of them are vulnerable to RowHammer from 70 degrees Celsius to 85 degrees Celsius. And we conclude that different DRAM cells are vulnerable to RowHammer within their specific temperature ranges. And we repeat the same analysis across all DRAM manufacturers that we test. There are 4 of them. And we observe similar distributions here. And here, okay, now we look at something different. So we make 2 observations across all these DRAM manufacturers. First, we observe that a significant fraction of vulnerable DRAM cells exhibit bit flips at all tested temperatures. So we conduct our tests in a range of temperatures starting from 50 degrees Celsius to 90 degrees Celsius. And we observe that, for example, here, 29.8% of the cells experience bit flips at all tested temperatures from 50 to 90 degrees Celsius. So there's a quite significant fraction of DRAM cells that are vulnerable at all temperature points. And the second observation is that we also see a small fraction of cells that are vulnerable to RowHammer at one particular temperature. So here, if you look at this annotated place, there are like 0.2% of the cells experience bit flips only at 70 degrees Celsius, but they do not observe bit flips at like higher or lower temperatures. Next, we study the impact of temperature on DRAM rows. And this figure shows how the number of bit flips in the victim row changes as temperature increases. So in the x-axis, we see the temperature values. And on the y-axis, we see the variation in bit flip counts normalized to the mean value at 50 degrees Celsius. So this is actually showing the delta in bit flip count. And we observe that more cells experience a bit flip with increase in temperature. So the general trend here is that as we warm up the chip, it becomes more vulnerable to RowHammer. And we repeat this analysis on all 4 manufacturers. And we see that 3 of them follow some similar trend. But, okay, I don't know why it didn't appear here. Okay. Okay, so if we look at the manufacturer B, we see an opposite trend, right? It's quite surprising. So if you get a DIMM from manufacturer B and then you heat it up, and then it becomes less vulnerable to RowHammer. So our takeaway is that a DRAM rose bit error rate can either increase or decrease with temperature, depending on the DRAM manufacturer. And in the paper, we also elaborate on this temperature analysis more, and we provide 3 more observations. The first one is DRAM rows can show either higher or lower HC first values when temperature increases. And HC first, or the minimum hammer count that you need to induce a bit flip, tends to generally decrease as temperature range increases. This is similar to bit error rate, right? So in general, HC first decreasing means you become more vulnerable to RowHammer. And when we look at the change in HC first, or delta HC first, it becomes larger when the temperature change is larger. Yeah, please go ahead.
So I can follow the intuition at circuit level why probably lower temperature gives less vulnerability because they have kind of less noise. Have you come up with an intuition of why on earth higher temperature could be better in some cases?
Yeah, so that's a fantastic question. I need to go to a backup slide for that. Just give me a second. Okay. So there is actually an earlier work that is based on some 3D TCAD model. It's purely simulation-based study. So they investigate the circuit level phenomena that cause RowHammer bit flips, and here they have 4 different charge trap models here, right? And they basically use like sweep some parameters basically here. And when you look at these models, you see like on the x-axis it's the temperature, and on the y-axis it is the okay, NRH in their terminology is HC first. In our terminology, it's the hammer count you need to reach to induce a bit flip, right? So if you look at like 250 Kelvin here, it says like, okay, look at the green one, for example. You need like some level like close to 150K hammer count, right? And as you heat up, the hammer count decreases, meaning RowHammer vulnerability increases up to some level, and then it goes constant at some range, and then it increases again, meaning that RowHammer vulnerability decreases. So it is not clear how or why it exactly happens this way, but based on this model, so this is basically some how can I say that, some trap model, right? Yeah, we need to actually go and explain all the details in this paper to explain it completely. But this is some circuit level phenomenon that causes the electrons to get stuck at some point, right? And this error mechanism itself has this particular feature that it can be better or like more effective at some temperature level and less effective at some temperature level, and we see this kind of curve. So our hypothesis here about like why there is this difference between these manufacturers is that maybe the manufacturing technology specific features in different manufacturers causes this trap model to execute in like this decrease in slope or increase in slope at like different temperatures. So you can basically offset this curve to right or left, right? So this is pretty much the explanation we could have found to this. I'm not sure if it's satisfying for you.
Yeah, thanks.
Okay. Let me see. Okay, I was here. I already talked about these. So yeah, so this is just a flash in the paper, and you can find more details, more discussions about this. You can find a more detailed discussion about the circuit level explanations as well in the paper. So are there more questions? Or okay, I'm moving to the second analysis, which is based on the aggressor row active time. So this analysis provides two key takeaways. First, as an aggressor row stays active longer, victim DRAM cells become more vulnerable to RowHammer. And the second observation is that, or takeaway is that RowHammer vulnerability of victim cells decreases when the bank is precharged for a longer time. And to conduct this analysis, we conduct two sets of experiments. So in the baseline, so this is a timeline, and we perform row activations and precharge back to back to do these activations, right? And in the baseline, we activate and precharge aggressor rows as fast as possible, as the DRAM standards allow. And in the second, in the first set of experiments, we increase the time where an aggressor row is active. So we activate, we wait longer time, precharge, and then we wait exactly the same amount of time as the baseline, and then activate again. So this is the first set of experiments, and in the second set of experiments, we do the opposite. We keep the row's active time constant, and then we just increase the time that the row or bank is precharged. And this plot demonstrates how bit error rate varies when aggressor row active time increases. And we observe that as the aggressor row stays active longer, more DRAM cells experience RowHammer bit flips. We observe the same trend on modules from all four manufacturers in this case. And yeah, if for a potential question, I can answer in advance, I guess. We explain this effect by referring to two different error mechanisms that are suspected to be causing RowHammer in the literature. One of them is the coupling between the word lines, and the other one is the electron injection. And you can see like one of them is more affected with the voltage swing in the word lines, and one of them is more affected in the when the from the electric field that is created between a word line, aggressor word line, and then some victim DRAM cells or victim word line. So this shows that I mean this mechanism is also being effective, and you keep the aggressor row active for longer time, basically. And for completeness, we also look at the minimum hammer count that we need to reach to induce bit flips. And on the y-axis, we see HC first, and on the x-axis, we see the aggressor row active time. And as you see, as the aggressor row active time increases, fewer activations are required to cause RowHammer bit flips. And we observe the same trend on modules from all four manufacturers again. So based on these observations, on the bit error rate and HC first, we conclude that as the aggressor row stays active longer, more DRAM cells experience RowHammer bit flips, and they experience RowHammer bit flips at lower activation counts. And yeah, so I'm gonna quickly skip the rest of this analysis, but I'll share a few other observations here. So the first one is so it's the other set of experiments, right? Doing the opposite. As the aggressor row stays active longer, this is just a statistical analysis. As the aggressor row stays active longer, the RowHammer vulnerability consistently worsens across tested DRAM rows. So it's a major trend. And when we do the opposite, the second set of experiments, we increase the time that a bank stays precharged longer. And when we do that, we observe that fewer DRAM cells experience RowHammer bit flips, and they experience RowHammer bit flips at higher activation counts. It's not very surprising, I think, because essentially what we do over there is we just increase the activation interval of these aggressor rows, so they are less frequently activated in some sense. And when we look at this behavior across individual rows, we also see that it consistently reduces. And yeah, please refer to the full paper for more details. Okay, third analysis is about spatial variation. So here we look at how RowHammer vulnerability varies across across different places in the same DRAM module. So we have two key takeaways from this analysis. The first one is the RowHammer vulnerability significantly varies across DRAM rows and columns due to both design-induced and manufacturing process-induced variation. And the second key takeaway is that the distribution of HC first exhibits a diverse set of values within a subarray, but similar values across subarrays within a DRAM module. So to do this analysis, we first investigate how HC first, or the minimum activation count to observe bit flips, varies across different DRAM rows. And on the x-axis, you see different DRAM rows sorted by reducing HC first value. We observe that HC first values and thus RowHammer vulnerability significantly varies across DRAM rows. So you see a huge difference between like the most vulnerable row and the least vulnerable row, and there's a huge variation of a variety of values across different rows. And when we look at all four manufacturers, we again see some different HC first values and a huge variation. So we conclude that the RowHammer vulnerability significantly varies across DRAM rows. And then since it's more relevant to the defense mechanisms, we focus on the most vulnerable 10% of the rows here. Yeah, it's 10%. And we observe that the most vulnerable 10% of the rows experience bit flips at activation counts about half the HC first of the rest of the rows. So I guess it's easier to see over there, for example, in the manufacturer D. When you look at the most vulnerable DRAM row, the activation count is like 43K. But when you look at the minimum value in like P90 or 90th percentile of the rows, then you see like the double of this hammer count. And this will become important when we start talking about the RowHammer defense mechanisms. So we conclude that a small fraction of DRAM rows are significantly more vulnerable to RowHammer than the vast majority of the rows. And second, we investigate how the RowHammer vulnerability varies across columns. And to do so, we generate a heat map plot of bit error rates across columns and chips. And we observe that bit flips, bit errors concentrate on certain DRAM columns, indicating that certain columns are more vulnerable than other columns, right? And as a next step, we analyze, we investigate how these columns vary across different DRAM chips. And to do so, yeah, we cluster each DRAM column based on its RowHammer vulnerability on average across DRAM chips, and the variation in its vulnerability across DRAM chips. And this plot again shows a population density for DRAM rows that follow a particular trend here. So if we want to give an example, so when you sum up all these values in this column, you reach to 16.7%, which is the fraction of the rows that show a high RowHammer vulnerability across all DRAM chips. And having this like similar high RowHammer vulnerability across all chips in a module indicates that there is some design-induced variation here, because these columns are consistently more vulnerable than other columns across all chips. And when you look at this rightmost set of DRAM rows, columns, there is a high variation in vulnerability across DRAM chips, and this occurs pretty much like random, and we conclude that this can be because of manufacturing process induced variation. And we again look at the distribution across all 4 DRAM manufacturers, and we observe that there exist columns with very low or very high RowHammer vulnerability or variation across DRAM chips. And based on this analysis, we conclude that both manufacturing process and design can affect a DRAM column's RowHammer vulnerability. So it is another thing to look into in future DRAM generations, right? Because if there is something inherent to the design, then we can fix it. Okay, yeah. About the spatial variation analysis, in the paper, we also analyze the variation across rows in a subarray and across subarrays in a DRAM module. And we make 2 observations based on this. The first one is the most vulnerable DRAM row in a subarray is significantly more vulnerable than the other rows in the subarray. I guess you have the concept of, you know what subarray is, right? Everyone else? Okay, nice. So basically, it's just like a set of DRAM rows within a DRAM bank, right? And there are like many subarrays in a DRAM bank. And when you look at the variation within a subarray, it looks like similar to the variation in a DRAM bank. And when we look at the HC1 distributions of subarrays within a DRAM module, they are significantly more similar to each other than those of subarrays from different modules. So it's really seems like you can actually get an idea about a DRAM module's characteristics by looking at a subarray. But yeah, I'm not going to cover that analysis in this presentation, but you can refer to paper, and you can always come talk to me or other co-authors as well. So now I will explain the implications of our observations for future attacks and defenses. Okay, so we believe that our observations can be leveraged to craft more effective attacks and to design more effective and efficient defenses. In the following slides, I will explain several examples of these implications. So as the first example, as an attack improvement, the attacker manipulates the DRAM module's temperature to increase the RowHammer vulnerability of the cells that store sensitive data. And we observe that DRAM cells are vulnerable to RowHammer in a bounded temperature range. So, and we call this vulnerable temperature range, if you remember this figure, right? And for example, an attacker can exploit this characteristics basically. And let's say this range is between like 50 degrees and 70 degrees Celsius. The attacker basically can warm up a chip or cool down a chip if it is like warmer or cooler than this vulnerable temperature range, and force the chip to operate in that vulnerable temperature range so that it can attack, right? So this is a very simple implication of attack. Yeah, please go ahead.
Can you increase or decrease temperature like programmatically by having a lot of requests to DRAM, and maybe it hits up the DRAM enough, or is that not realistic at all?
I think in theory it makes sense. Yeah. We didn't try it basically, so I cannot say something definitive for this particular DRAM chips. Yeah, but I think in theory you can. So there are some operations that drain a lot of current, right? So row activation is basically one of them. So there is a chance, yeah, if you can do a lot of operations in a very short amount of time, you know, drain a lot of current, then you can. But I'm not sure what would be the significance of that temperature change. So I guess in this attack scenario, we just assume that the attacker has a physical access to the device and just like connects a heater or like, you know, puts a AC or something like that. Yeah. So in the second attack example, the attacker uses RowHammer to understand the DRAM chip's current temperature. So we find this a little bit more interesting actually. As an example, more than 76% of the cells are vulnerable to RowHammer above 70 degrees Celsius for manufacturer C. And focusing on these cells, an attacker can identify if the DRAM temperature is above 70 degrees Celsius. And it can be a sign of abnormal operating conditions that might occur during a data center in its peak hours, for example. Or this information can be used to trigger an attack. Basically, in this particular example, you can attack a data center in its peak hours based on this. So this is basically not an attack itself, but to trigger an attack. And let's assume another case where it's important to precisely measure what the temperature is. And even in that case, you still have a smaller fraction, but you still have some cells that experience bit flips only at 70 degrees Celsius. So you can use these cells and understand that if the temperature is exactly 70 degrees Celsius. And this is not particular for 70 degrees Celsius, right? You have these kind of cells in pretty much every temperature. Yeah, basically, this is the attack model. So there's a third example. Is there a question? No. Yeah?
Don't these temperatures also depend on the device that you're employing? So you would also have to know which devices are present now.
Yeah, exactly. So I guess in that kind of scenario, you should either characterize that device somehow. So it can be a case where, like, I don't know, maybe you're a vendor or like distributor, you characterize your chips and then sell them, you know? And then you can just like match which one is that. Or you can also use like some trends that are specific to some manufacturers. You can estimate with some accuracy. Well, this second one wouldn't work in that case, I guess, because you need some precise measurement. Yeah, but yeah, good point. So this attack model is not particularly like very strong. It requires a lot of assumptions for the attacker. So the third one, an attacker can leverage the effect of aggressor row active time, as we showed, like when in this scenario, instead of activating aggressor row as frequently as possible, the attacker can keep the aggressor rows active for longer times, and it is possible by just issuing more read requests, for example, to a row so that it can stay active longer. And based on our analysis, HC force reduces by around 36% when you use this kind of access pattern. And with this reduction, an attacker can easily bypass RowHammer defenses that do not account for this reduction, because this is something we found out recently, right? And if your defense mechanism deployed on your system does not account for this, and it is calibrated for some minimum hammer count that is some large, you know, and then you can reduce it by 36%, and boom, you can just flip it. It's really great. Okay. So we also have some improvements for defenses. And I will explain two of them here, but you can find more in the paper. The first improvement leverages the variation across rows. And we observe that different rows have different HC first values, right? So 90% of the rows only experience bit flips at like double the hammer count of the most vulnerable 10%. And if we can basically exploit this heterogeneity in like many other works in other fields. So based on our analysis, basically, if we exploit this heterogeneity in calibrating the recent RowHammer mitigation mechanisms, we can reduce the area overhead of, for example, BlockHammer by 33% or graphene by 80% using this heterogeneity. So this is one improvement to defenses. And the second one is, the second example leverages the variation in RowHammer vulnerability with temperature again. And again, we have the vulnerable temperature range here as a reminder. And we show that DRAM cells experience bit flips in this bounded temperature range, right? So if we want to avoid bit flips, let's say we operate at a temperature level, which is here, for example. And within this temperature level, we know that row A is vulnerable, for example. And then we can basically disable row A at this temperature. We can use another row instead of row A. And probably you know that there are like these redundant rows for improving yield in this bank, right? Or you can maybe just like reduce your usable address space, and you can just swap in, swap out some DRAM rows based on what temperature you're operating at. And by doing this, you can actually make your whole system more reliable, basically. And yeah, these were the two examples, and we have more things in the paper if you're curious. So the first one is leveraging the similarity across subarrays in a DRAM module can reduce the module's profiling time for RowHammer errors. The second one is monitoring and limiting the aggressive row active time from the memory controller can reduce the RowHammer vulnerability and make defenses more efficient. So this is again going back to the effect of aggressive row active time, right? And yeah, so it is a consistent trend across all manufacturers that when you keep aggressive rows active for longer, then you're more vulnerable to RowHammer. So how can you reduce that? It's really hard to reduce it in the DRAM chip. So maybe you can have some mechanism that communicates between the DRAM row, DRAM chip and the memory controller. And in the memory controller, you can easily track like which row is stayed active for how long, right? Because you have the memory scheduler, you're the component that actually issues these requests. So you can actually do something smart over there. So these are all future work anyway. And another option is ECC schemes that can target the non-uniform bit error distribution caused by design-induced variations across DRAM columns. And yeah, as the last defense improvement, we can suggest cooling DRAM chips because it has some general trend of reducing RowHammer vulnerability. And yeah, you can refer to the paper for more details. So to conclude, denser DRAM chips are more vulnerable to RowHammer, and understanding RowHammer is critical to find effective solutions. However, no rigorous study demonstrates how this vulnerability varies under different conditions. And in this work, our goal was to provide insights into 3 fundamental properties of RowHammer that can be leveraged to design more effective and efficient attacks and defenses. The first one was DRAM chip temperature. The second one is the time that an aggressive row stays active. And the third one was the victim DRAM cell's physical location. And we conducted this study by doing experiments on 272 DRAM chips from 4 major manufacturers that implement DDR3 and DDR4 DRAM standards. And we provide 6 key takeaways from 16 novel observations in the paper. And from these, we highlight that RowHammer bit flip is more likely to occur in a bounded range of temperature when the aggressive row is active for longer time and in certain physical regions of the DRAM module under attack. And we conclude that these observations can inspire and aid future work to craft more effective attacks and design more effective and efficient solutions. And that concludes my talk. Okay, so I can get more questions if there's any. Yeah, please.
Yeah, on the general, I guess, not a methodology of how to get the results, but rather of how you wrote the paper. In earlier RowHammer papers, we saw that I think people were very conservative with actually releasing the manufacturer names, the mapping between ABC and Hynix, Samsung, and so on.
Yeah.
And I think you showed them, right?
Yes. So in this paper, we revealed them.
Can you comment on why the change of heart?
So I'm not sure if Onur wants to jump in.
Yeah, maybe I will jump in. Yeah, I think Well, I think the vulnerability is very well known at this point, and the trends are very similar across many vendors in this particular case, right? I mean, there are some differences, of course, but I think it's good for researchers to build on these trends at this point and validate the results as well as figure out new things, right? So I think today, which is 7 years after the vulnerability was first exposed publicly with our paper, is a different time than in the past. And I think it makes sense to show like the different the chips that we have tested. I don't know, maybe Giray has also some other opinion on this, but that's the main reason, right? This is a very well-known problem at this point, and it's important to see for the reproducibility of the research. Now, this doesn't mean that the prior research was not reproducible, right? Clearly, even though we did not directly reveal ABC in our original RowHammer paper and maybe later RowHammer papers, people clearly reproduced the work and built like tens, if not more than 100 papers that show that this is real. So I don't think reproducibility is a problem, but this makes it easier for future research to build on the work, as well as for manufacturers to also see the trends that they may not know, right? I'm actually not sure if the manufacturers know everything that we have exposed in this paper. So it's good if they know some of the things that we have shown actually.
Thanks.
Sure.
Yeah, as Onur says, it's even if we anonymize them, we say that these are major manufacturers, right? And you can just search like statistics about like which manufacturer is selling how much or having what percentage of the market. It's like almost 100% anyway, shared by these like 3-4 manufacturers. So, and some of these observations are actually common across all those manufacturers. It also doesn't make any like much difference actually, you know, because you can, so you see some trend, and if this is Micron or Samsung or Hynix or was for fun Mania, they're all the like pretty much same. So it's kind of revealing itself actually. Okay. Any other questions? If there's not, I'm gonna move to BlockHammer, or
Yeah.
is it a good time to take a break maybe?
I don't think we have time to take a break like yesterday. Sorry about this, but if people need some bio break, they can perhaps do it, let's say asynchronously.
Asynchronously, okay.
Like whenever they want to, basically, let's say. And yeah, please do that, anyone who needs it, while I introduce the next work. We're already running actually late today also. I was hoping we would cover all 5, but I think we're going to defer at least one. But it's good, I think people are asking questions, and that was actually the main purpose of these research talks, so that people can ask questions about cutting edge research that's going on, and people can see like what cutting edge research is like. And I think these are 2 papers that were presented in October. And you can see the details of the analysis and how detailed the analysis is. These papers basically push the boundary of RowHammer research to new unexplored areas that no one has been to. And it's good to, of course, brainstorm what comes next, right, after this research. And if you're interested in this, certainly you can talk with people who have been presenting the papers and the co-authors, certainly Hasan and Giray, because there's more to do in this area for understanding RowHammer. And also, I think I must mention that earlier someone was bringing up like since you publish these papers, don't manufacturers get angry or something like that? I would argue that it should be the opposite if anything should happen, right? Because these products are clearly having issues, right? If something gets bit flips, perhaps people should hold the manufacturers to a higher standard and say that, okay, we don't want these bit flips because they're going to affect our lives, right? So I think maybe I don't quite understand the mindset that leads to the question of like manufacturer defending themselves even though their product is not working correctly, right? So I think it's good to maybe correct that mindset also. I would argue. Because if the product is not obeying the specification, right? The specification never says you're supposed to change a value in a location that you're not even accessing, right? That's wrong by any definition of memory operation. Okay, I wanted to correct that because I think that's important to also think about. I think I also gave you some kind of break by giving this, let's say, short discussion. Okay, now let's move to the last talk on RowHammer, and again we're going to switch gears a little bit and talk about defense protection mechanisms. And this was work published at HPCA this year in February. So this is also a very recent work, as you can see, and it is as far as we know, the state-of-the-art mechanism for defending against RowHammer. It's called BlockHammer, preventing RowHammer at low cost by blacklisting rapidly accessed DRAM rows. And Giray is going to present this work which he led. Giray, please go ahead.
Okay, thank you very much for the introduction. So I'll quickly move to the executive summary. So in this work, in this work, we tackle RowHammer again as a worsening DRAM reliability and security problem. And the problem we are tackling is that mitigation mechanisms have limited support for current and future DRAM chips. And this has two components, basically. One is scalability with worsening RowHammer vulnerability. And the second limitation of the mitigation mechanisms is compatibility with commodity DRAM chips. And our goal here is to efficiently and scalably prevent RowHammer bit flips without knowledge of or modifications to DRAM internals. And our key idea in this mechanism is to selectively throttle memory accesses that may cause RowHammer bit flips. And our key mechanism here is called BlockHammer. BlockHammer tracks activation rates of all rows by using area-efficient Bloom filters, throttles row activations that could cause RowHammer bit flips, and identifies and throttles the threads that perform RowHammer attacks. And by doing so, BlockHammer provides a full DRAM full defense against RowHammer attacks, and it is competitive with state-of-the-art RowHammer mitigation mechanisms when there is no attack, and it is superior in performance and DRAM energy consumption when a RowHammer attack is present. And we analyzed BlockHammer in various ways, and we show that BlockHammer does not require any proprietary information of DRAM internals and no modifications to DRAM circuitry. So it is both scalable and compatible solution. Okay, so I will skip DRAM background to save some time and directly go to the motivation and goal. So there are 4 high-level RowHammer mitigation approaches that we can identify in this work. In prior work. The first approach is to increase refresh rate very naively, and which this reduces the refresh window and thus the activation count that an attacker can reach in a refresh window. The second high-level approach is to physically isolate potential victim rows with sensitive data from aggressor rows that a potential attacker can hammer. And to do so, they allocate isolation rows in between these victim and aggressor rows such that the attacker cannot disturb sensitive data by performing RowHammer attack. And the third approach is reactive refresh. In reactive refresh, when an aggressor row is hammered, potential victim rows are refreshed to avoid bit flips. And finally, the fourth approach suggests throttling or slowing down the memory accesses proactively, such that no row's activation rate can reach to a RowHammer threshold to induce RowHammer bit flips. So I will talk about two challenges that these mitigation mechanisms are facing. So the first challenge is scalability with worsening RowHammer vulnerability. Recent work showed that DRAM chips become more vulnerable to RowHammer in the last decade, as I showed in the previous presentation as well. So RowHammer bit flips can occur in much lower activation counts, and hammer in a row can disturb more rows than before. And furthermore, in-DRAM mitigation mechanisms are shown to be ineffective. And therefore, RowHammer is a more serious problem than ever today. And to address this scalability, worsening DRAM, to address this worsening RowHammer vulnerability, increasing refresh rate approach requires refreshing all rows more frequently, and it is not sustainable due to a large number of rows that needs to be refreshed. And the second high-level approach, physical isolation, requires allocating more isolation rows, which costs more DRAM capacity. Reactive refresh needs refreshing more potential victim rows and refreshing them more frequently. And proactive throttling needs to slow down the system furthermore. So we conclude that all these mitigation mechanisms face the challenge of scalability with worsening RowHammer. The second challenge is compatibility with commodity DRAM chips. And to understand this challenge, we need to revisit how memory addresses are mapped to DRAM cells through several abstraction levels. In the application level, we have virtual memory addresses. Then typically the system software translates these virtual addresses to physical addresses. And so far, all these, then these physical memory addresses is mapped to some logical addresses of DRAM channel, rank, bank, row, column, right? And so far, all these address translations are visible within the processor itself. However, there is an additional address translation that takes place in the DRAM chip itself called In-DRAM mapping. And here, it gets the logical addresses and maps them to actual physical rows and columns. So DRAM manufacturers or vendors apply this In-DRAM mapping for two reasons. The first reason is design optimizations to simplify DRAM circuitry to provide better density, performance, and power. And the second reason is improving the yield by mapping faulty rows and columns to redundant ones. So this In-DRAM mapping scheme includes insights into chip designs and the manufacturing quality, and that's why DRAM manufacturers prefer to keep it as proprietary information and they do not share it. So when we look at all these four high-level RowHammer mitigation approaches, actually we should look at two of them here, namely physical isolation and reactive refresh mechanisms. These two high-level approaches intrinsically need to identify victim or isolation rows in each of them to be able to understand, like when a RowHammer attack is happening, which rows should we allocate for isolation or which rows we need to refresh. And this definitely requires this proprietary knowledge, and we do not have access to this knowledge, basically. Our goal in this work is to prevent RowHammer efficiently and scalably without knowledge or modifications to DRAM internals. And I will, based on this, I will start explaining BlockHammer now. So the BlockHammer's key idea is to selectively throttle memory accesses that may cause RowHammer bit flips. And BlockHammer consists of two mechanisms. namely row blocker and attack throttler. Row blocker tracks row activation rates using area-efficient Bloom filters, blacklist rows that are activated at a high rate, throttles or enforces a certain delay between activations targeting a blacklisted row. By doing so, row blocker ensures that no row can be activated at a high enough rate to induce RowHammer bit flips. And the second part of the mechanism, attack throttler, it identifies threads that try activating blacklisted rows and reduces their memory bandwidth consumption by throttling their memory requests. And by doing so, attack throttler greatly reduces the performance degradation and energy wastage a RowHammer attack inflicts on a system. I will explain how row blocker works next. So row blocker modifies the memory request scheduler to throttle row activations that could lead to bit flips. To do so, it blacklists rows with high activation rates and delays subsequent activations targeting them. And we call the blacklisting logic row blocker BL, or blacklist, and the delaying logic row blocker HB. HB stands for history buffer. To throttle row activations with a high activation rate, row blocker blocks a row activation if the row is both blacklisted and recently activated. And in the slide, I'll explain how row blocker operates in high level. So the first memory request scheduler pings row blocker with is the row activation RowHammer safe request or query before performing the row activation. And row blocker simultaneously checks both of these structures. If a row is blacklisted and recently activated, then it returns a signal saying that RowHammer this request is RowHammer unsafe. So if this is the case, memory request scheduler does not issue the row activation, and the activation is blocked basically. And meanwhile, this activation is blocked. There are probably other requests waiting in the queue, and they're being serviced as usual. So when the memory request scheduler issues a row activation eventually, both components are updated with the row activation information basically. Okay, so let's dive into the blacklisting logic. Row blocker BL, or the blacklisting logic, tracks row activation rates and blacklists a row when its activation count in a time window exceeds the threshold. So to do this in an area efficient way, it employs two counting Bloom filters, which are area efficient counting structures. So I'll explain how a counting Bloom filter works in our mechanism, basically. So a counting Bloom filter is essentially an array of counters here. And we address these counters using some hash functions. And when a row A is activated, its row ID is provided to a set of hash functions that evaluate a set of indices to counter array, and each of which is incremented 1. When we activate another row, row B, it increments another subset of counters. But as you see here, so this is not like perfectly distinct, and there can be some overlaps for different row IDs. These hash functions can map to some particular counters, and they are incremented more than the actual value. So that's one limitation of the Bloom filters, basically. Therefore, we can observe a row's activation count more than its actual value. That leads to false positives. And when we want to estimate a row's activation count, we test row A, which again goes through the same hash functions and then addresses these counters. So we get the minimum value among these counter values and get the activation count based on that. So since we do not decrement these counters at any time, they're just incrementing, we cannot observe activation count value less than its actual value. So there's no false negatives here. But since we do not decrement them, now we have another challenge. These counters can saturate because they are not like infinitely large. And we use a time interleaving approach, and we employ 2 quantum balloon filters to periodically reset them without losing information. That I will explain that next. So, okay, so Blacklisting logic employs 2 quantum balloon filters, and a new row activation is inserted in both filters at all times. But only one of these filters responds to test queries at a given time, and we call that filter active filter, and the other filter is passive filter. And the active filter alternates at every epoch between these 2 filters. And let's look at the operation of 2 filters, CBFA and CBFB, across the timeline shown here. So yeah, we see CBFA and CBFB here. So let's say a green bar indicates that a balloon filter is active at this given epoch, and we use the gray bar to indicate that it's passive. So only one of them is active at a given epoch. So let's start with the from the beginning. We start as like CBFA is active and does not blacklist the row for the first some number of activations until the activation count reaches a threshold that we call blacklisting threshold. Okay, at timestamp. Okay, yeah. So row blocker blacklists a row if the row's activation count reaches this value, basically. And assume now that the row, so this is for one single row, right? That what we are showing here. Assume that the row is activated at a high rate in this first 2 epochs, and at a low rate in the 3rd epoch. And okay, so we start from the beginning, and we keep activating the row, and this blue bar shows that this blue bar shows that the row is not blacklisted yet, but at timestamp 2, the row's activation count reaches actually the blacklisting threshold, and we start blacklisting the row. And from now on, this red bar shows that the row's counter exceeds MBL or blacklisting threshold, so that we keep blacklisting threshold until the end of we keep blacklisting the row until the end of the epoch. And when we reach the timestamp 3, the active filter CBFA is cleared, or like all counters of this balloon filter is reset to 0. And we switch to CBFB, the other balloon filter. And now this filter is responding our test queries. And this filter is not reset at this point, right? And it remembers the activations from epoch 1. So it keeps blacklisting the row until the end of epoch 2, because the row's activation count also exceeded the blacklisting threshold based on the CBFB's records. And at CBF4, at timestamp 4, let's say we keep activating this row, right? And CBFA's counters were 0 at this point, and then it remained at blue up to some level, and then at timestamp 4, CBFA's counters also exceed this blacklisting threshold. So it also, when tested, it also says that we need to blacklist this row. And let's move to this timestamp 5. At the end of epoch 2, we clear CBFB as well. So we reset all the counters to 0. And now we switch back to CBFA. And CBFA keeps blacklisting the row again, because, excuse me, its counters exceeded MBL at timestamp 4. And yeah, remember we assumed that the row is not activated at a high rate at epoch 3. So CBFB's counters do not exceed the blacklisting threshold until the end of epoch 3. even though the row is blacklisted during epoch 3. And when finally we switch back to CBFB at timestamp 6, the row is not blacklisted anymore because based on CBFB's records, it is not supposed to be blacklisted. So this is basically how we switch between these two counting Bloom filters and sustain the security guarantee of no false negatives while resetting some counters here and avoiding saturation. So to ensure RowHammer safe operation, RowBlocker limits the activation rate of blacklisted rows at a RowHammer safe level, right? And an activation rate is RowHammer safe if it is smaller than or equal to RowHammer threshold or RH activations here. You can also think of it as like HC first activations in a refresh window based on like different papers, different terminology. So RowBlocker limits the activation count RowBlocker limits the activation count of a row to NCBF in a CBF. So here what we see what we say by lifetime is, so we clear CBF A here, for example, in this point, and then we clear again at that point. So this is the lifetime of a CBF, and RowBlocker limits the activation count of a row to some value in this CBF time window. And as long as this activation count to this time window ratio is, or when we say like activation rate is below the RowHammer threshold, then we are safe, right? So mathematically, we can actually express it like this. So I don't want to get into math too much here in this presentation. You can check the paper. We have a section about security analysis, and we can talk more and go through these steps one by one later, at other time other than lecture. But yeah, for now, you can just say that, okay, if my activation count and CBF in a TCBF time window is smaller than NRH activations in a TRFW or refresh window, we are RowHammer safe. And to sustain that, so again, we have a timeline here of as wide as a Bloom filter's lifetime. And we can fit like NCBF row activations here. And let's see how this delay logic works based on this history buffer. So we have like very frequent row activations, right? In the worst case, we can have a row activation at every TRC time. And this is specified by the DRAM standards, basically. So to reach the blacklisting threshold, NBL, the soonest time or shortest time we can reach this blacklisting threshold is TRC times NBL, basically. And when we reach to NBL row activations, now after this point, until the end of this time window, we have this much of time, TCBF minus TRC times NBL, right? And as I showed like in the previous slide, after this point, we basically blacklist the row. So what are we going to do with the blacklisted rows? This is the question. We show a blacklisted row activation in red color here. And what we do is basically we introduce, we enforce a delay between the row activations here. So up to this level, we allow the row to be activated as frequently as possible, basically. But after it is blacklisted, now we enforce this T delay such that the total number of activations is not going to exceed the RowHammer threshold. And to ensure that, we can basically compute this T delay based on this formula here, because it is the number of activations over there. And we have NBL activations here. So this total thing should not exceed RowHammer threshold. And as we increase T delay, we can have less number of activations. So this is the knob that we are playing with to throttle the row activations, basically. Okay. Yeah, I think I explained everything here, unless you have questions. No, okay. Okay, so row blocker, HB, or history buffer ensures that no subsequent blacklisted row activation is performed sooner than this T delay time window. And to do so, it implements a history buffer that contains the information of all row activations that can fit in a T delay time window. And a blacklisted row activation is blocked as long as a valid activation record of the row exists in the history buffer. So, excuse me. So what row blocker does is it queries this history buffer, right? And if it can find a record that is valid, it means that we already activated this row in the past T delay time window. So we should blacklist it because it is not RowHammer safe if the row is blacklisted. We should block this row activation. So with this mechanism, no row can be activated at a high enough rate to induce RowHammer bit flips. So we deterministically ensure that no row can exceed this threshold. Okay, so I covered row blocker, and I'll quickly cover attack throttler, hopefully. Attack throttler tackles the performance degradation and energy wastage that the RowHammer attack causes. And to identify and reduce the negative impact of RowHammer attack, attack throttler leverages the observation that a RowHammer attack intrinsically keeps activating blacklisted rows. That's the ultimate goal of RowHammer attack, right? Because it cannot induce bit flips without activating blacklisted rows. To this end, attack throttler introduces a new metric called RowHammer likelihood index. And this is basically the number of activations that target blacklisted rows normalized to the maximum possible activation count. And if we look at the value that this RowHammer likelihood index can get, for benign applications that do not activate blacklisted rows, this value is basically 0. And it reaches to 1 if a RowHammer attack is running on a system, basically. Because now we reach the RowHammer threshold when it's 1, right? Because we perform blacklisted row activations as much as we can. And if there is no BlockHammer in the system, then you can even exceed 1. You can perform more activations. So the conclusion of this slide basically is RowHammer likelihood index is larger when the thread's access pattern is more similar to a RowHammer attack. And now we use this as a metric to identify the RowHammer attack threads. So attack throttler applies a smaller quota to a thread's in-flight request count as RHLI increases. So if the thread is benign, then we do not apply any quota, basically. And if the RowHammer attack is running and it reaches to like this kind of RowHammer likelihood index, then when it reaches 1, then after this point, we do not allow any request from this thread. Basically, we just like stop the thread over there. And by doing so, BlockHammer or attack throttler reduces a RowHammer attack's memory bandwidth consumption. And this enables a larger memory bandwidth to concurrently run in benign applications. And by doing so, it greatly reduces the performance degradation and energy wastage a RowHammer attack inflicts on a system. And RowHammer likelihood can optionally be used as a RowHammer attack indicator by the system software. If you have some other sophisticated malware detection systems and stuff, you can flag them saying that, oh, this thread is doing something wrong. Okay, yeah, this is basically what the mechanism is, and I'll move on to evaluation. So first, we analyze and compare BlockHammer's hardware complexity with 6 state-of-the-art RowHammer mitigation mechanisms, namely Para, ProHit, MRLock, CBT, Twice, and Graphene. So we calculate the hardware complexity in terms of area, access energy, and static power consumption. And we use a realistic RowHammer threshold of 32K of the time. And yeah, we observe that BlockHammer is, it can be considered as a low-cost mechanism, and it is competitive with the state-of-the-art counter-based mechanisms, which are CBT twice and graphene. And to understand how hardware complexity of BlockHammer and the other mechanisms scale with worsening RowHammer vulnerability, we repeat the analysis for a RowHammer threshold of 1K. So we extremely decrease the RowHammer threshold here. I think so far among the chips we characterize, I don't remember any RowHammer threshold that is as small as 1K. So this is really some like future-looking kind of analysis. Yeah, this we project this for the future chips. And we compare how the complexity of each mechanism changes in terms of chip area. Yeah, here chip area, access energy, and static power consumption. And we observe that BlockHammer's hardware complexity scales more efficiently than state-of-the-art RowHammer mitigation mechanisms. And BlockHammer, yeah, okay, I already said that. So as the second step of evaluation, we conduct cycle level simulations using remulator and DRAM power to evaluate the performance and DRAM energy consumption. And we simulate a realistic system with a DDR4 DRAM module that is specified here. I'm not going to go into detail. We evaluate our system with this set of single core benign workloads that include some spec CPU benchmarks, some YCSB disk carrier requests, some network accelerator traces, and some synthetic traces that performs bulk data copy with non-temporal hint. So on top of that, we use we randomly choose a set of these single core benign workloads and run them together as 8-core multi-threaded, multi-programmed workloads. And we randomly generate like 125 workloads that contain 8 benign applications. And we also analyze another 125 workloads that each of which contain 7 benign applications and 1 RowHammer attack thread. So we started evaluating for single core benign workloads, and we classify single core workloads into 3 categories based on their row buffer conflicts per kilo instruction. And we evaluate the performance and DRAM energy consumption for BlockHammer and 6 state-of-the-art RowHammer mitigation mechanisms, basically. And we observe that no application's row activation count exceeds BlockHammer's Blacklisting threshold when it's run in single thread. And therefore, BlockHammer does not change the performance or DRAM energy consumption for single core benign applications. So it's similar to some other state-of-the-art mechanisms. Yeah, the overhead is practically 0. And things get more interesting when we evaluate these mechanisms with multi-programmed workloads, 8-core workloads. So we conduct this test when there is no RowHammer attack, as I said earlier, and when there is a RowHammer attack is present. So we use 4 metrics in this evaluation to demonstrate the system throughput in terms of weighted speed up and job turnaround time in terms of harmonic speed up, unfairness in terms of maximum slowdown, and DRAM energy consumption at the very end. So these are the values basically. Okay. So here we conclude that when there is no attack in the system, BlockHammer introduces very low performance and DRAM energy overheads. And these are the numbers that I just pulled from the paper. You can see more detailed results over there. And when there's a RowHammer attack present, then BlockHammer significantly increases benign applications performance by 45% on average and reduces DRAM energy consumption by 29% on average. And this is all because of throttling the malicious RowHammer attack thread without affecting the other applications, and other mechanisms don't do this. So we conduct a scalability study with worsening RowHammer vulnerability here. Again, for the cases when there is no RowHammer attack and when there is a RowHammer attack present. And we scale the RowHammer threshold from 32K to 1K. On the x-axis, you can see how the RowHammer threshold changes. And here are the results for system throughput, job turnaround time, unfairness, and DRAM energy consumption. So we observe that BlockHammer's performance and energy overheads remain negligible, even when RowHammer threshold is scaled down to 1K. And BlockHammer's scalability provides much higher performance and lower energy consumption than state-of-the-art mechanisms when there is a RowHammer attack present. So we have more analysis in the paper, including a security proof where we mathematically represent all possible access patterns and show that no row can be activated at a high enough rate to induce bit flips when BlockHammer is configured correctly. Second, the paper explains how BlockHammer addresses many-sided attacks by tuning its thresholds. Third, we evaluate all 4 high-level RowHammer mitigation approaches through analyzing 14 mechanisms. You can see over there in the second column from 4 aspects: comprehensive protection, compatibility with commodity DRAM chips, scalability with worsening RowHammer vulnerability, and deterministic protection. And we show that BlockHammer is the only mechanism that satisfies all of them based on the criteria we explain here. So to conclude, this paper tackles RowHammer as a worsening DRAM reliability and security problem, while state-of-the-art RowHammer mitigation mechanisms face limitations, supporting current and future DRAM chips due to limited scalability with worsening RowHammer vulnerability and limited compatibility with commodity DRAM chips. So the goal of this work is to efficiently and scalably prevent RowHammer bit flips without knowledge of or modifications to DRAM internals. And our key idea is to selectively throttle memory accesses that may cause RowHammer bit flips, and our mechanism BlockHammer performs 3 operations to achieve this. It tracks row activation rates of all rows using area-efficient Bloom filters. It throttles row activations that could lead to RowHammer bit flips, and it identifies and throttles the threads that perform RowHammer attacks. And we evaluate BlockHammer's scalability with worsening RowHammer and demonstrate that BlockHammer is competitive with state-of-the-art RowHammer mitigation mechanisms when there is no attack in the system. And BlockHammer provides significantly higher performance and lower DRAM energy consumption when a RowHammer attack is present. Also, we look at BlockHammer's compatibility, and we show that BlockHammer is compatible with current and future commodity DRAM chips because it does not require any proprietary information of DRAM internals or modifications to DRAM circuitry. So this is basically what BlockHammer is. And yeah, I can take your questions now, if there's any. Right.
I guess a point to the evaluation, you show that even with 1,000 hammer threshold, you only have like some 0.7x weight speed up, right? I think that's roughly the number.
I can go back. Which plot are you talking about?
So, oh, okay, no, that's not even. So we show almost no slowdown, in fact.
Yeah.
So, I mean, I think past RowHammer papers talk about some workloads which almost, like benign workloads, which almost exhibit naturally a BlockHammer, RowHammer behavior, right?
So which paper is that? Did you say?
It might be, I don't know, like the RowHammer in like looking back at RowHammer. I don't know what it's called anymore.
I see. Okay. So I think it highly depends how you configure your system as well. So for a benign application to reach to that hammer count, actually first your row buffer locality should be terrible, for example. And it also depends on how you map your row data into different DRAM rows, columns, banks, and stuff, right? And so here, what we use is basically like state-of-the-art configuration used for improving row buffer locality. And In this configuration, we basically, how can I say that? So it's not like just sequentially writing the data into a different row from beginning to end, for example. So you put a bunch of data in some place in a row, and then you move to another bank, and then put some other data over there. It's called like interleaving. You can do this interleaving in like cache line granularity or like several cache line granularities. And we also apply this mechanism called, what was it? I guess minimalistic open page. Based on the row ID, you also change the sorting of these data in different banks. So one row goes from like bank 0, then bank 1, then bank 2, for example, and then another row goes like bank 2, bank 5, bank 0, something like that. And this is what is shown to be good for improving row buffer locality, and it is implemented in like many systems today. So when we use that kind of configuration, we do not observe that any of these benign applications reach into RowHammer threshold, basically. But if we don't apply these techniques, then yeah, we can observe those. Yeah, I did that analysis, so I can confidently say that. But yeah, so you can still argue that there can be some benign applications that maybe reach to that threshold, but we do not test here, right? Because we cannot test like every single application in the world. And yeah, if you can find that paper and share it with me, that would be really great, actually. I'd like to reproduce the results.
Yeah, thanks for the answer. It was either mentioned in the lecture or in one of the papers, but I really have no idea where anymore.
Okay.
I think I've heard it as well from Onu. Like I think he talked about like he saw some applications exhibiting like some RowHammer behavior or something. I don't know if he wants to jump in.
Yeah, so I guess you can observe some like behavior of like activating the same row again and again. So if maybe you can be remembering that from, I don't know, works like Crow maybe, or charge cache. So there's a behavior called row buffer temporal locality, row level temporal locality, and over there it's some like observed trend that when an application actually activates a row, there's a high chance that it's going to activate the same row again in like near future, and you can actually consider that as like hammering, right? Yeah, but yeah, in my experience, I didn't see like they reach to like up to RowHammer threshold, because for RowHammer you need to reach some large hammer count in a very short amount of time. But in this kind of behavior that I explained about like row level temporal locality, usually you see like this row is being activated in, I don't know, in the next microsecond or something like that. I don't know if anybody remembers from the audience, maybe. Other questions?
Like this kind of seems too good to be true, actually, this paper. Like, is this going to be implemented then? Because it really seems like there's no bad side, right?
Well, it is not cheap, right? So here I showed some area complexity, for example, hardware complexity. So it is one of the like drawbacks of this mechanism, I would say. I mean, nothing is, I mean, there's no free lunch anyway. So you need to pay for some area or energy, you know, those kind of things. And I don't know, it can be implemented in the real systems. Based on our analysis, it seems like it works really good. Yeah, but for sure we don't know what they implement, right? And this is just published in like early 2021, in like March or so. I wouldn't expect to see this in real systems this soon, I guess. Yeah, it depends on your constraints, I guess, as the processor designer. So it can be like just a little thing to pay, or it can be too large. I don't know.
I guess the burden is then on who has the burden of implementing this then?
So we propose this as a completely memory controller based mechanism, right? So memory controller is placed in the processor die. So it would be like, let's say Intel or AMD, you know, those kind of companies should be implementing this. But there's also another trend in the industry. So when you go ask the DRAM manufacturers, they say that, oh, there's no need for this because, you know, our chips are like RowHammer free. We do the all security precautions and stuff. And then Hasan comes and hacks all of them. So. Any other questions? Comments? Okay, I guess that's the end then.
Okay, maybe we should move to Minesh's talk also, even though I realize we will go over time, but I think I would really like to cover Minesh's talk because this is the he can give this talk in person as opposed to online later, and it's much better to cover it in person. I don't know, is it ready, Giray, or?
Yes, I downloaded the slides.
Okay, sure, yeah. Yeah.
Okay, it's open in the wrong place.
Yeah, so I think while you're doing that and while Minesh is getting ready, maybe I'll make comments on BlockHammer. I think certainly this is a secure solution, as Giray demonstrated, but it doesn't come for free, right? It's always good to try to come up with even more lower cost and more efficient solutions. So we'll see if, I believe this is a good solution, but I think research still needs to continue on lower cost and secure solutions going into the future. And one of the benefits of BlockHammer type of solutions is, I think, its ability to identify reasonably accurately attacks, and it could communicate with the operating system. Oh, I believe this process is not behaving normally, so do something about it. And Giray in the paper shows that it's accurate. And always, I think testing more workloads would help. That was part of the discussion. I don't know if a lot of work covered benign workloads, but there's certainly anecdotal evidence. This is not published, but anecdotal evidence that there's some very, very, very rare workloads that induce RowHammer bit flips in real systems. But this, I think we discussed this in one of the RowHammer lectures, but this is anecdotal in industry. And I think the results of, let's say, a BlockHammer kind of shows that also, right? We don't see any workload that, let's say, loses a lot of performance. And that kind of shows that these workloads are probably very, very rare. But there's no guarantee that they don't exist, and there might be workloads that actually, especially when technology scales and the RowHammer threshold reduces, there might be workloads that get close to, there might be benign workloads that get close to inducing these bit flips. Okay, I think with that, let's move to Minesh's talk. This is also another paper from Micro this year, which is last month. And Minesh recently defended his thesis, and this is the fourth major piece of work that went into his thesis. He had 5 pieces of work that was part of his thesis. And this is the fourth one, let's say. Maybe in the future, he will give an overview of the entire thesis at some point later, but not today. So he will look into memory error mechanisms as well, but not necessarily RowHammer. He will describe what he will look into, but he will describe a HARP, practically and effectively identifying uncorrectable errors in memory chips that use on-die error correcting codes. So far, we've been discussing issues with memory chips that do not have error correcting codes, but if you actually have memory chips with error correcting codes, that actually complicates error profiling significantly, and he will talk about that. And Minesh, please go ahead.
All right, thanks, Owner. Yeah, so I think Owner gave a pretty good introduction, so I'll jump right in. So the motivation of this work starts with state-of-the-art memory error mitigation mechanisms typically require the processor, or in particular the memory controller, to identify which bits are at risk of error, and we refer to that process as error profiling. And so the problem that we tackle in this work is that on-die ECC complicates the process of error profiling by changing how errors appear to the memory controller. And so the goal in this work is to understand and address the challenges that on-die ECC introduces for the profiling process. And so to achieve this, we have two main contributions. First, we analytically study on-die ECC's effects on profiling, and we identify three key challenges that on-die ECC introduces. So first, on-die ECC exponentially increases the number of at-risk bits that the memory controller needs to identify. Second, on-die ECC makes individual at-risk bits much harder to identify. And third, on-die ECC interferes with commonly used memory data patterns that profilers commonly use. And second, we introduce hybrid active-reactive profiling, or HARP, which separately identifies raw bit errors and those errors that are introduced by on-die ECC. And in doing so, HARP effectively reduces the problem of profiling a memory chip with on-die ECC into that of profiling a memory chip without on-die ECC. And so in our evaluations, we demonstrate that HARP overcomes all three of the challenges that I mentioned earlier. And HARP identifies all errors faster than two baseline profiling algorithms, which sometimes actually fail to achieve full coverage of at-risk bits. And second, we provide a case study that shows that HARP identifies all errors faster than the best performing baseline by 3.7x as an example result. And so our artifacts are available at GitHub, which is essentially allows you to reproduce our evaluations. And so this is an overview of my talk. And so I'll start out talking about general memory error mitigations and profiling. So let's talk about, the title is covered up there. Okay, so we'll talk about scaling related memory errors first. So as memory manufacturers continue to scale memory density, this generally increases memory error rates for a variety of different error mechanisms. And so here I show three different error mechanisms that are taken from DRAM. And so the first is data retention, which Hassan introduced in his talk. Essentially, it's charge loss in cell capacitors. The second here is write recovery, which is the amount of time that it takes to actually write data into a cell. And third is variable retention time, which I believe Hassan also mentioned. It's where a cell's retention time changes over time unpredictably. And so all three of these are technology-specific phenomena that cause errors in DRAM. And in particular, all three of these manifest as uncorrelated single-bit errors. And these are typically accepted to be the primary DRAM technology scaling challenge today. And so we're focusing on these single-bit errors in this work. And so let's take a look at how we might deal with these increasing single-bit error rates. So the higher error rates generally require more and more sophisticated solutions. And so here is a sort of a graph showing for different error rates along this axis, ranging from very low error rates, 10 to the minus 14, to very high error rates, 10 to the minus 4. And this essentially represents the number of errors that occur within the device. And so this is taken from a prior work, which sort of describes which types of mitigation mechanisms you might want at different error rates. And so on the left here, we have relatively low error rates, which were sort of in the past at this point. And at these error rates, you either don't need to have any mitigation mechanism, or a simple mechanism like row and column sparing suffices. And so row and column sparing is essentially where you take a faulty row and replace it with a good row, or same with a column, right? And so today, the error rates are sort of getting into this regime where we need some sort of error correction mechanism that's stronger than what we had in the past. And so typically we're using single error correction mechanisms today. And so on-die ECC in particular is what we're going to talk about in this work. And so I'll talk more about it later. And in the future, error rates are projected to get even higher. And there we need more advanced solutions, which we'll also talk about. Okay. So first I'm going to start off just giving an overview of a typical on-die ECC design that we use today. And so what's typically incorporated in DRAM chips is a 128-bit single error correcting Hamming code. And so I'll illustrate this in the context of a DRAM chip, right? So here we're illustrating an external DRAM bus, which communicates with the CPU. And so when the CPU performs a write operation, it first interacts with the chip IO logic inside the DRAM chip. And the IO logic actually breaks up this communication into 128-bit pieces. And so each 128-bit word, it first goes through ECC encoding logic, which adds some additional metadata along to these 128 bits. So you end up with 8 additional metadata bits for a total of 136 bits, and that's what gets written to the data store. And so when the CPU does a read operation, that entire 136-bit region is read out and decoded, and the decoder uses that metadata to potentially perform a correction operation. And therefore, the data that's returned through the chip IO to the external DRAM bus is the corrected data, right? And because it's a single error correcting code, it's capable of correcting a single error within the 128 region. But if we end up with more errors in the data store, then undefined behavior ensues, depending on the particular mathematical function used by the encoder and decoder. And so that's what we'll talk about later in the work. But as it stands today, this is sort of what on-die ECC looks like. And there's 2 important properties to note here. So first, this on-die ECC is fully contained within the DRAM chip. And because of this, it's completely invisible outside of the chip. And so the memory controller and CPU and so forth are unaware that on-die ECC even exists. Okay, so now let's move on to talk about these more advanced error mitigation mechanisms that I referenced. So in general, error mitigation is a huge research space with solutions that span from the software all the way to in-memory, as we just saw. And so just to give some examples, in software, we have mechanisms like page retirement, where we look at things in terms of virtual memory pages, task replication, where we do redundant operations, and so forth. Within the processor, we have bit repair mechanisms, which I'll talk about more soon, error correcting codes in general, including ones that are much stronger than on-die ECC, as I just described. And in memory, we have row column sparing and on-die ECC. And so in this work, we're dealing with, so the cost and efficiency of which mechanism you actually want to use depends on the particular errors that you want to mitigate. So if we're dealing with single bit errors, perhaps something like an error correcting code is more appropriate. But if the error model looks different, then you might choose something else. But yeah, so in this work, we're going to focus on these bit repair mechanisms because we're focused on these addressing these single bit uniform randomly occurring errors that are related to technology scaling. Okay. So let's take a closer look at the memory repair mechanisms then. And so a memory repair mechanism essentially identifies and repairs any bit that is at risk of error. And at risk of error means that it could fail constantly, it could fail sometimes, it exhibits an error at some point. And so here's what a repair mechanism sort of looks like. And so on the right here, I'm illustrating an unreliable memory. So this could be DRAM, it could be something else. But essentially, it has an error-prone data store that is prone to these scaling-related errors. And so then in the memory controller, we have the repair mechanism, which itself contains an error profile. And you can think of the error profile as just a list of at-risk bits, right? So the repair mechanism's job is to repair any bit that's marked in the error profile as at risk. And so when the CPU performs a write operation, the data first goes through the repair mechanism before being written to the data store. And on a read operation, the repair mechanism first repairs any potential bits that are marked as at risk before returning that data to the CPU. So the problem here is that the repair mechanism needs to know which bits are at risk in order to do its correction operation. And this process is determined through error profiling. And so let's look at an error profiler. So there are 2 main types of profilers that we deal with. And so the first is shown in red here, which is the active profiler. And this profiler induces worst case testing conditions in order to try and make errors occur. And in this way, it's trying to achieve high coverage of at-risk bits. The other type shown in green is what we call reactive profiling. And the reactive profiler just passively monitors the memory chip to try and capture errors as they are observed during runtime. Now, regardless of which type of profiler we use, they both check for errors, and then they mark any observed errors as at-risk bits within the error profile. And then we simply repeat this process until all errors are identified, or more realistically, until we have enough confidence in our results. And so this is general profiling. And the point I want to make here is that this whole process, regardless of which profiler you use, it requires observing the at-risk bits to fail, because only then do you know that this bit is at risk of error. And so now let's take a look at what profiling a memory chip with on-die ECC looks like. So on-die ECC, unfortunately, changes how errors appear to the profiler. Right? And this is because if we have this diagram from before, we have the profiler interacting with the memory, But on.ECC here interposes between the profiler and the error-prone data store. And it does so in a way that is unclear to the profiler, right? Because it's invisible. And so the question we want to ask is, how does on.ECC actually affect the error profiling process? And so our goal in this work is to understand and address any challenges that on.ECC introduces for profiling. Yes.
So when you talk about profiling bits that are at risk, what exactly are you talking about? Are you talking about bits inside of these 128-bit windows or inside rows? Or I'm not sure I get exactly where this all happens.
That's a great question. Sorry, I haven't used this particular PowerPoint interface before. Just trying to go back to a slide that I presented with the on-days. Yeah, so here. So I think I'm actually going to talk about this more in the next couple of slides. But just to quickly clarify, from the processor's perspective or the memory controller's perspective, all they really care about is the external DRAM bus, right? So you write some data, you read some data, whatever comes back here is really the only thing that's relevant. And so when you're profiling, you're worried about what's happening on this bus, right? And so when we're talking about an at-risk bit, from the processor's perspective, any bit that could potentially fail on this bus is considered at risk, right? And so while if we didn't have on.ECC, it's exactly what's happening in the data store. Like I read from a particular location and I observe an error, that's what'll appear on the bus, right? And so you can think of a correspondence between the two. But when we have something like on.ECC in the way, what's happening in this region is not necessarily what happened in the data store. And so what you observe here is actually what happens here, right? So at some level, you're profiling what's happening here if there is on.ECC in place. And I have some examples in the next couple of slides to talk about that. So, yeah.
It's at risk of what?
Just like a bit flip, right? Going from 0 to 1, 1 to 0.
So no, it's not attacked by RowHammer or anything. It's just like naturally flipping.
Yeah, that's fair. So I was talking about in the beginning slide, I was talking about these scaling related memory errors, right? So these are, I guess you could say, sure, just naturally happening, right? You could exacerbate these through malicious activity. Like, if we crank up the temperature, these guys become more common and so forth. I think, you could extend this and sort of apply it to something like RowHammer, but it doesn't exactly apply in terms of the profiling process that we're describing here. It's okay. So I presented this profiling algorithm, right? This general sort of thing. And so this assumes that errors are sort of repeatable and they happen in the same place, and you can actually discover them through profiling, right? So if you have an error mechanism that satisfies that criteria, you could apply this sort of methodology to it. And so RowHammer could potentially be like this, but I think we're not 100% sure about that because we presented some experimental methodologies before. I think we don't know enough about the errors really to claim that this is the best approach. Yeah. Okay, perfect. Yeah, go ahead.
Another related question about the why of profiling. So suppose we got this to work, we got the profile. What kind of operation could the processor then do to correct the bit? So my understanding is we only know this bit would be one that's likely to flip, but we don't know much more.
Mm-hmm. No, that's a great question. I think that, I guess I didn't go specifically into what exactly this repair mechanism is doing, right? So I think that's what your question comes down to. We have this nice error profile, but what do you do about it? So this actually depends on the context quite a bit. So I think one great example is with data retention errors. You could imagine a mechanism where, we are going to sort of refresh weak rows more often, right? And so this is an example of a repair mechanism because the mechanism, in this case, it would be the refresh logic or something like this. It knows which rows are weak, which is essentially the information in the error profile. And then it will act on that to refresh them more often, thereby mitigating any potential errors that occur. Right? So that's in one context. And at that point, you're not profiling individual bits, you're profiling entire rows, right? But you could imagine something where it goes at the granularity of something much smaller, right? Like you could profile individual bits here, and then in the read data, the repair mechanism's job is to, when the data is originally written, if it's known to be a bad bit, you don't actually write it to the data store. you write it to some other memory within here, or you write it to a known good location of the data store, something like this. There's actually tens of these in the literature, and there's lots of creative solutions and so forth. But I think, does that give you a general idea?
Yeah, definitely. Thanks.
Yeah. So the point so the reason we're focusing on this is because if I go back to this plot, it's this region that we're expecting in the near future, right? We want to enable memory scaling to these sorts of high error rates, because otherwise, what do we just not make smaller chips? I mean, that's not great. I mean, we look at other technologies, sure, but if we have a way to efficiently enable this operating point, that would be great, right? And so this sort of bit repair really falls under advanced solutions. Mm-hmm. Okay, I'll move on then. Perfect. Okay, so yeah, so the next part here is where we're looking at on-die ECC's impact on error profiling. So I'm going to walk through a few examples next. So let's look at profiling a memory chip, right? So again, the profiler's goal is to identify all bits that are at risk of error. And so here I'm showing a memory chip without on-die ECC. And essentially what's happening is that at the external interface, the raw data is visible, right? So exactly what's happening in the data store is exactly what's visible outside. In contrast, if we have on-die ECC, what's visible outside at the interface is actually what we refer to as post-correction data, because the raw data has been through the on-die ECC logic and it's been corrected. And so you don't observe exactly what's happening in the data store. And so from the profiler's perspective, the profiler has no idea what's happening in the data store because it's within the memory. It only observes what's happening at the interface. And so the profiler marks any bits that are observed to fail at the interface as bits at risk of error, right? And so this is talking about bit granularity profiling. You could imagine the same thing for some other granularity, right? Okay, so let's take a closer look at without on-die ECC. So if we don't have on-die ECC, there's really only one potential source of errors, and that's when the underlying physical bit exhibits an error. So here I'm simplifying things to just show, let's suppose in the memory chip, we have 4 data bits, and I mark the bit as E if it exhibits an error, or in gray dash if there's no error. And so in this 4-bit pattern, we have 2 bits that fail with an error, right? And so what we observe outside is exactly the same thing. We observe out of these 4 bits, 2 of them failed, and we refer to this type of error as a direct error because the same errors are observed both inside and outside the DRAM chip, right? And so the profiler observes these 2 bits to fail, and it marks these bits as at risk of error. And so the error profile is computed as the union of all direct errors observed. So this gets more complicated with on-die ECC because now there are 2 different sources of errors. And so here I showed a memory chip that uses on-die ECC. And so again, it's a simplified representation, right? Not the 128-bit code, but let's say in this example, we have 4 data bits and 3 metadata bits, right? And so the metadata is used for error correction only. So another nuance is that this is called a systematic encoding. And so what we're assuming is that the data is not transformed by the on-die ECC function. So when we write the data, it's written exactly as is, and the metadata bits are just appended. And this is a very reasonable assumption for actual devices because it reduces energy consumption, provides debugging capability, and it's typically what people do. So in this type of system, let's say we observe this error pattern at the interface. So so I'll talk about the 2 different types of errors, right? So we again have this direct error, which corresponds to the exact bit position within the data bits. And so again, this appears before and after correction. However, we have another type of error here called an indirect error. And this occurs when on-die ECC mistakenly corrects a bit. And this is all because on-die ECC is dealing with an uncorrectable error pattern, right? If this is a single error correcting code, we have 3 errors to deal with. So on-die ECC performs some undefined operation based on the exact mathematical function it implements. And so in this example, it injected another error here, thinking there was an error. And so, yeah, okay, so it's called a miscorrection. But basically, we have these 2 different types of errors. And so the profiler observes these 2, and it believes that these are bits that are at risk of error. And so now the error profile is computed as the union of direct and indirect errors. Okay, so let's look at these indirect errors a little more because they're very significant to what we're doing in this work. So an indirect error fundamentally depends on the raw bit error pattern that occurs. So here I'm replacing the E for error with X meaning at risk, right? So now this bit may or may not fail, but it does fail sometimes, right? So now what we're dealing with is combinations of errors. And so as an example, we could have two potential patterns, one where all three of these at-risk bits fail, and one where just two of them fail, right? And so the problem is that, okay, so yeah, so let's suppose both of these go through on.ECC, and we call them pre-correction before, post-correction after. The problem is that these two result in two different patterns after correction, right? And this is because even though it's the same on.ECC logic, there's a different pattern of errors before correction. And so here, the direct errors are in the same position because they correspond to the same underlying error, but the indirect errors are in different positions because they are a function of which errors happened to occur, right? And this is purely a function of the on.ECC logic acting on a particular error pattern. So, okay, so the key observation we make from this is that any particular bit can actually be at risk of indirect errors given different combinations of raw bit errors, right? And so it's not limited to just which physical bits might fail. It's actually, a function of what ECC decides to do. And so this means that on.ECC introduces some sort of statistical dependence between bits that are otherwise independent of each other. Yes.
So I haven't seen these systematic encodings before. So it's not just pictorial here that you show direct errors stay in the same position. This is actually happening in truth, because I don't think it's standard for other error correcting codes, right?
Right. So it's a design choice. Like you can choose to use the systematic encoding, in which case, yeah, you get this correspondence where if there was an error at any of these positions, you would observe the same error here, unless on.ECC happened to correct the error. But you absolutely do not need to use this type of encoding. You could just have some function of all 7 bits to create something else that doesn't correspond. But so this is what I was saying, like typically in these memory devices, we use this type of encoding because so for example, imagine that you're going to do a read operation. In the common case, you won't have an error, right? Well, assuming you're operating at relatively low error rates. So then all you need to do is just return these to the IO pins. There's no data transformation necessary. So you save on energy, you save on latency, and it's just generally desirable. But yeah, I mean, you don't need to do it this way. So this is an assumption that we're making. Yeah. Okay. Yeah. Does that clarify? Okay. Perfect. So yeah. So essentially, this statistical dependence is a big problem, and so I'm going to talk about that a little more. So because of this dependence, we identified 3 different challenges that on.ECC is causing here. So first, on.ECC exponentially increases the number of at-risk bits that the profiler needs to identify. And this is because even a small set of at-risk bits can create a combinatorially larger set of post-correction at-risk bits. Second, it becomes harder to observe each of the individual at-risk bits because every particular indirect error depends on a raw bit error pattern. And only when that raw bit error pattern occurs do you actually observe the indirect error. And third, on.ECC interferes with data patterns that we use for testing, because now these data patterns need to consider combinations of errors at the entire word level when previously they did not. So I'm going to talk about each of these 3 in a little more detail. So first, we're looking at the combinatorial explosion of errors. And so the key principle behind here is that n at-risk bits can fail in 2 to the n ways, right? And so if we have this picture from before, where I labeled these errors 0, 1, 2, we have 8 possible patterns that can occur depending on which of these at-risk bits decides to fail. And so we have 2 to the 3 patterns, right? And so these 4 here are correctable because they have 0 or 1 errors, assuming a single error correcting code. But these are uncorrectable, right? And so in the worst case, each of these 4 can introduce a unique indirect error. And so every uncorrectable error pattern can potentially cause a unique indirect error, right? And so this is the combinatorial explosion. So this would result in an exponential increase in the number of at-risk bits that the profiler needs to identify. And so this table here, I just summarized the very worst case scenario that can happen. So if we have n bits pre-correction, we can end up with 2 to the n bits post-correction. And yeah, I mean, as expected, these numbers explode from like 4 to 15, 8 to so forth. It's just a much harder problem because you have so many more bits to identify. The second challenge here is identifying the at-risk bits themselves. And so indirect errors, as I was saying before, only appear for specific ECC-dependent combinations of pre-correction errors, right? And so this makes them really hard to identify because you have to identify them one at a time. And this process is slow and time-consuming. The problem here is that the profiler cannot see or control the pre-correction error pattern that occurs. And so even though it wants to systematically find them all one at a time, it doesn't have control over which pre-correction errors manifest. Like whatever happens in the device happens, and the profiler simply responds to that. And so this, again, is like a slow and difficult process. And yeah, so I said that already. So this sort of slow exploration, we're saying can only really be overcome by transparency into the on-die ECC at this point. In some sense, we're saying that the memory controller needs the ability to see past the on-die ECC and actually see what's happening in the physical bits. Otherwise, it can only infer what's happening based on what it sees after correction. Okay. And finally, the third challenge deals with these data patterns. And so profilers typically use different data patterns to exacerbate different errors. And so, here we might write 0 and 1s in rows, or in columns and rows and checkerboard and so forth. And these patterns induce worst case circuit behavior, which tries to maximize the chance of observing an error. And so on-die ECC interferes with these. So let's take a little look. So on-die ECC breaks these in two different ways. So first, there's a carefully designed test pattern, but once it goes through on-die ECC encoding, it becomes obfuscated within the memory device, right? And so previously we mentioned the systematic encoding. So potentially a portion of this data is preserved as is in the physical device, but the parity check bits, which will be appended, those are now determined as a function of the on-die ECC instead of the carefully designed pattern that the user provides. And if we don't have a systematic encoding, then all bets are off and the whole thing could be just obfuscated. And so now, even though the tester wants to exercise some particular failure mode that this pattern exacerbates, what's going to happen in the memory device is not that. And so the testing is sort of confounded. And the second problem is that these types of patterns typically induce single bit worst case conditions, because we're looking at an individual bit and its neighborhood and sort of doing the worst case for that. And the problem is that with on-die ECC, multiple bits need to fail at once in order to cause a particular indirect error to occur, let's say. And so the worst case pattern needs to consider all of the bits in an entire ECC word. And multi-bit data patterns in general are very difficult to design and use. And we discussed that a little bit more in our paper and mentioned some prior works that deal with it. Okay, so yeah, we've talked about these three challenges. So now let's talk about HARP, which tries to overcome these three challenges.
Minesh,
yes.
Can you hear me?
Yes.
There's a zoom controls on top of your screen. I would suggest getting rid of that. If you go to more, I think you can hide the controls.
Yeah, do you want? Okay, that's much better. Thanks, guys. All right, so yeah, so let's move on to HARP, which is addressing these three challenges. Okay, so HARP is based on a very simple key observation, and it's that these indirect errors really are a byproduct of on-die ECC, essentially the error correction process. And so here I'm showing the same diagram we've seen before. And so although any number of direct errors can potentially occur, only one indirect error can occur at a time, assuming, again, this is a single error correcting code. But the point here is that the indirect error count is upper bounded by the ECC algorithm, right? So for an n error correcting on-die ECC, at most n indirect errors can occur at a time, right? And by at a time, I mean on every read operation, basically, right? So this is the key idea behind HARP. And so we use this to propose identifying direct and indirect errors separately, right? Because the indirect errors are bounded. And so let's take a look at how we do this. So I'm going to talk about HARP here, which implements this using a sort of two-phase profiling algorithm. So the first phase uses active profiling. And the goal here is to quickly identify all direct errors. So in this phase, we're ignoring indirect errors entirely. So here I'm showing the memory controller and the memory chip again. And this red logic here represents the active profiler. And it uses an ECC bypass path to directly read data from the data store. And so what this means is that it's completely ignoring the metadata, and it's just reading the data bits themselves and profiling those data bits to try and find direct errors. And whenever a direct error is identified, it's reported to the error profile as the profiler does. The second phase consists of reactive profiling, which tries to identify the indirect errors, ignoring the direct errors that have already been found. And so this is performed using a secondary ECC, which I guess maps well to the on-die ECC, such that if the on-die ECC, if it's an N error correcting code, the secondary ECC is also an N error correcting code, and it can capture any indirect errors that might occur. And so in this way, by first doing active, then reactive profiling, HARP identifies all of the at-risk bits that exist. So I'll talk about these two phases in a little more detail. So I zoom in here on the just the active profiler design. And so again, we have this ECC bypass path that is used by the active profiler to directly read from the data store. And so just to describe a little more, this ECC bypass path does this only for read operations, right? So when the active profiler performs a read operation for profiling, the memory returns the data bits and completely ignores the ECC metadata. And for this reason, the ECC bypass is a very simple sort of low overhead change to the device, because this doesn't require any sort of data transformation or changes to the granularity of data or anything like that. It's just returning the data without performing the correction operation. So you can think of it as just skipping the correction operation, right? We just bypass the decoder. And so as an additional point, this bypass path enables us to use existing profiling algorithms to identify bits that are at risk of direct error, as if there's no on-die ECC at all, right? So here, we can essentially think of this as just not having on-die ECC, right? And so as a result, this active profiler reduces the task of profiling a memory chip with on-die ECC into a task of profiling memory chip without on-die ECC, given minimal modifications to on-die ECC. But recall that this is not sufficient because we still have the indirect errors that we need to deal with. And so that's what the reactive profiler then deals with. And so the reactive profiler consists of the secondary ECC, which then basically after all the direct errors are already being repaired, the upper bounded indirect errors are then captured by the secondary ECC. And so here it becomes a little complicated because the system designer needs to choose a suitable secondary ECC to do this. And there are several design concerns here. Okay, I guess, so the design concerns include things like matching the granularity of these two codes, because yeah, so we have this large design space, and the requirement that HARP imposes is that the secondary ECC needs to be able to correct N errors per on-die ECC word, given that on-die ECC is an N error correcting code. So the ECC word here is what needs to be dealt with here as well. And so the system designer needs to take that into account when choosing an appropriate secondary ECC. Because in a more complicated case, there's not just one memory chip here. Like we've seen in the past that memory modules contain 8, 16, 32 chips. And so then each of those on-die ECC words needs to be protected by the secondary ECC in order to do effective profiling. But it is a very large design space because it depends on both how the on-die ECC is designed, how many chips there are, and a lot of other factors that I guess we talk about in the paper. Oh yeah, I guess I mentioned that a little bit. Okay, any questions to that point? Okay, I'll move on. So as another sort of optimization to the reactive profiler, we observed that, so the reactive profiling is fundamentally quite slow because we can only observe indirect errors one at a time, right? It's for every uncorrectable error pattern that occurs, there could be a different indirect error, and we have to wait to capture all those. And so what we can do is that we observe that we can shorten this whole process by anticipating the indirect errors that might occur, given that we've already done active profiling and identified some direct errors. And so what this means pictorially is that if we already know that a couple of bits are at risk of direct errors, if we know the actual on-die ECC implementation, which is the mathematical function that it implements, we can predict that, in some combination of errors, it is possible to have an indirect error here or here and so forth. So we can pre-compute, let's say, some of the indirect errors given bits that are known to be at risk of direct errors. And so for that reason, we introduced two variants of HARP, where we have HARP aware and HARP unaware, one which does know the on-die ECC parity check matrix and one that does not. Okay. So that completes my overview of HARP. And so I'll quickly talk about the evaluations that we have. So so our evaluation methodology is that we use Monte Carlo simulation to evaluate this. And the reason we do so is because this enables us to accurately calculate coverage. So it's a little bit subtle, but in this type of on-die ECC case, coverage is very difficult to estimate because depending on which pattern, which errors happen to occur, you have different at-risk bits. And so it's it's not a straightforward computation to figure out which bits are actually at risk of error and what proportion of those have been identified. And so we use a SAT solver to do that, and it becomes a very expensive process and so forth. But it's actually feasible to do. Whereas if we had a real experimental setup, we can't observe what's actually happening, and all bets are sort of off. So yeah, we perform simulation, and we simulate a large number of representative ECC words. Our artifacts, which represent essentially the simulator, is open source on these websites. So we compare against two different baseline profiling algorithms. So the first is what we refer to as naive, which is just one of these round-based profilers that completely ignores the possibility of on.ECC. So it just treats the memory chip as if on.ECC does not exist. And so here, every round of profiling uses a different data pattern, which, for example, random data or something. And then the profiler marks any observed bits at risk of error. The second baseline is BEEP, which comes from our own prior work, which sort of studied this problem in the past, but in a different context. And so BEEP knows the exact on.ECC implementation, which is, again, this mathematical function. And it follows a similar sort of strategy to the naive mechanism, but it crafts its data patterns by being informed of the parity check matrix. And in doing so, it can sort of try and make indirect errors easier to find. So these are the two baselines we compare against. And so first, let's take a look at the coverage of direct errors that the active profiler enables. And so here is sort of the results that we have. And so there's a lot of different curves here. But so along the x-axis, we're showing the number of profiling rounds that are required to achieve a direct error coverage of the y-axis, right? So high coverage means that we found all of the bits. Low coverage means we haven't, right? And so each of these different curves represent the three different mechanisms, right? So we have HARP, naive, and BEEP. And the different curves themselves have markers, which represent different numbers of pre-correction errors we inject in our simulation. So for example, if we look at the 5 curve, which is illustrated with the dot, we inject 5 errors into the ECC word, but those errors are probabilistic themselves, right? Which is why we have these 4 different panels. So these 5 errors fail with probability 25%, 50%, and so forth. So we refer to that as the per bit probability of pre-correction error. So there's a lot of stuff here, but so I want to make 2 key takeaways, I think. So, okay, so first, HARP achieves full coverage in all of the cases, outperforming both of the baseline algorithms, right? And we see that with the green curves always reaching the 1.0 mark. As a side point, BEEP actually fails to achieve full coverage of direct errors because it's not actually exploring different pre-correction error patterns. It's choosing specifically patterns that result in indirect errors, and therefore it's not getting good coverage of direct errors. The second point is a little sort of, I don't know, harder to see, but HARP is independent of the number of pre-correction errors. And you can see this by the green curves all being exactly the same for all of these different pre-correction error counts. And the reason this happens is because the HARP essentially is using this ECC bypass path to directly observe errors. So it doesn't matter how many errors there are. They're all being independently identified, whether there's 1 or 10 or however many. And that's a really important point because the other profilers aren't able to do that, right? When there's more errors, there's more combinations that need to be explored to achieve high coverage. So they end up with a large spread of curves. And so these two really show that HARP overcomes these 3 profiling challenges by separating the direct and indirect errors. And so the next I want to show is the profiling speed evaluation. And so here we're again dealing with the direct errors. But the goal in this analysis is to look at how many profiling rounds are necessary to prevent n-bit error patterns from occurring, right? So this sort of at this point, okay, sorry, I think I misspoke earlier. So at this point, we're ignoring the distinction between direct and indirect errors, right? We're just concerned with n-bit error patterns that could theoretically occur. And the reason we want to look at this is because that's what the secondary ECC needs to protect against, right? So if an n-bit error pattern is possible, then secondary ECC needs to have at least n-bit error correction. And so for this particular graph I'm about to show, we inject 2 raw bit errors per ECC word, and these errors fail all the time, right? So the per bit error probability is 1.0. So here is the data from this particular plot. And so on the y-axis here, I'm showing the maximum number, sorry, the x-axis, the maximum number of simultaneous post-correction errors that are possible, given a y-axis number of profiling rounds. So what this means, for example, is that if we have an x-axis category of 1, this requires a single error correcting code to protect against all remaining errors after this many profiling rounds have elapsed, right? And so we're ignoring the distinction between direct and indirect errors. This is just any possible pattern that can occur. And on the other end of the spectrum, x-axis category of 6 means that it requires a 6 error correcting code after this many rounds of profiling. And so what we want to take away from this plot is that HARP only needs 3 rounds to prevent multi-bit errors from occurring, right? So assuming a single error correcting code, after 3 rounds of profiling, only these indirect errors remain that HARP can identify using the secondary ECC, which is not true for the baseline algorithms because they require potentially orders of magnitude more rounds of profiling to achieve the same level of coverage of these error patterns. And so here we expand the analysis to these different numbers of pre-correction errors per word and different probabilities of pre-correction errors. And it's just a lot of data. But the main takeaway is that HARP achieves very high coverage of at-risk bits much faster than the baseline algorithms. And as an example result, if I highlight this particular 50% point, HARP performs 20 to 62% faster than the best performing baseline in order to achieve this sort of single error correcting coverage. Okay, and the final result I want to present is this case study that we do on DRAM data retention. And so here we consider a system that uses an ideal repair mechanism, which means that we assume that it perfectly repairs all bits in the error profile. And so we study how the end-to-end system bit error rate changes when using the different profilers. And so this is the results we obtain, where again, we show the number of profiling rounds on the x-axis, but this time on the y-axis, we're showing the bit error rate after this many rounds of profiling and applying the secondary ECC, right? So we do all the indirect profiling, we do all the reactive profiling to identify the indirect errors. And so what we observe here is that HARP always reaches 0 bit error rate for all of these curves, right? And when the per bit error probability is relatively low, it takes many more profiling rounds, whereas when it's very high, so it's actually not visible on this plot, but essentially in the first round, it's already identified all of the direct errors because they occur with probability 1, so they're immediately visible. But anyway, so HARP very quickly reaches the 0 bit error rate value, whereas BEEP fails to achieve this at all because it never achieves full coverage of the direct errors. And so a single error correcting code is never sufficient to achieve 0 bit error rate. And as an overall takeaway, HARP reaches 0 bit error rate 3.7x faster for this particular configuration as an example result. And so finally, I want to conclude with just, we have more stuff in the paper, including a detailed analysis of on-die ECC, a discussion about the design choices we make, more evaluation results, and a detailed description of our evaluation artifacts. And so take a look at the paper if you're interested. And our artifacts are available on these websites. And so I'll just quickly recap this. So our motivation here is that these state-of-the-art error mitigation mechanisms typically require error profiling, but on-die ECC complicates the profiling process. And so our goal is to understand and address the challenges that on-die ECC introduced for profiling. And to that end, we first analytically study on-die ECC's effects and we identify these challenges. And then we introduce HARP to overcome these 3 challenges. And in our evaluations, we demonstrate that HARP overcomes these 3 challenges effectively, and it's faster than the best performing baseline algorithm. So I think that concludes the talk. So yeah, do you guys have questions at this point? Please.
So is it infeasible to profile ECC DRAM without changes to the hardware architecture?
Yeah, I think that's a really good question, right? Because so this question of feasibility is very subjective at some level. So I think what we show here is that, okay, so let me go to one of these slides real quick just to go to this result, right? So in this case study, right? So I think you can see here that if you look at this orange curve, I guess the laser point, okay. Yeah, if you look at this orange curve, this is the naive mechanism, right? So the naive mechanism does not make these hardware changes. It's just profiling the on-die ECC chip as is. And you see that, in these cases, it still does eventually reach 0 bit error rate, which means that essentially if you waited for this many profiling rounds, you still get full coverage with that mechanism, right? So it's not like it doesn't work. It's not impossible. It's just a much more difficult problem because it requires much longer. And I think the other point to make is that this in general is sort of an idealized picture of how things happen, right? Because we're doing this simulation-based study where we're injecting these really nicely behaved errors with very fixed error rates and so forth. in the real world, you'll have a big mix of different types of errors and so forth. And so we get this whole extra level of complication from errors that are just hard to find for any profiler, like ECC or not ECC. If an error is not repeatable, or it occurs with some very strange characteristics, or it's very low probability, it's going to be hard for any of these profilers to identify it. And then the question comes up, is it even something that you should be dealing with using profiling? Or should you have some other mitigation mechanism that doesn't rely on profiling? So I think between those two concerns, it's such a big space in the error mitigation world to sort of figure out what's right, what's feasible. I think what we're demonstrating here is that by being aware of the ONDA-ECC and making the changes to bypass it and everything we described, for this case that we're describing, yeah, it does become much easier. But I wouldn't try to argue that it is feasible or infeasible either way.
I see, thanks.
Mm-hmm. Please.
It seemed a lot of the, I guess, performance gains you have is from the getting the direct errors quickly, right? So you need this bypass thing, and you said it's cheap to do because you just take the data straight away. Mm-hmm. But don't you need extra interconnects? Isn't that expensive?
Yeah, so let me go back to this figure with the this ONDA-ECC diagram at the beginning. I think so when we talk about the bypass path, essentially we're saying from here to here, we skip the decoder, right? So I think at some level, we cannot answer that question because we don't know what the manufacturers actually do, right? So we suspect that that path already exists for debugging reasons, because as soon as the manufacturer builds the chip, they need to test whether it's working. And so they have the same problem, right? Now ONDA-ECC is interfering with their own testing. And so they very likely have their own bypass paths to just directly read from the data store, skip all of this or disable it or something, and then test whether the chip works. So we've actually seen evidence that such a bypass path exists in some other non-DRAM devices, like other memory chips. I think for an STT-RAM product, actually, if I'm not mistaken. But these sorts of paths do exist in some chips. We have no idea what they do in DRAM, but it stands to reason that they probably do something similar. But yeah, if they don't, then yes, I agree that some amount of changes are necessary, and it's hard for us to quantify the impact of those changes. Like in theory, it should be, you could just bypass like the logic that does the correction, right? You could do every other operation, still do the decoding, but just the step that corrects the error that it found, skip that one step. The cost of that depends on how you implemented the logic and everything. So it's very difficult to say, I think. But so if nothing else, there have been prior works that propose doing something very similar. So both patents and academic publications that also request a bypass path for other reasons, I guess. So yeah, and I think we believe it's the bare minimum that we could ask for. And we chose this bypass path because we think out of all the alternatives, it is sort of the simplest, but that depends on the implementation in the end. Yeah, sorry if that's not as satisfying as it could be. Yeah, okay. Are there any other questions then? Okay. Well, yeah, then I think we're done. So thanks, guys. Owner, do you want to jump in?
Yeah, I think I'll jump in. Thanks, Minesh, for presenting. And I think we're done. Yeah, unfortunately, we're already over time, and we will not be able to get to the Quark TRNG work. I think we'll try to arrange another session to cover that. But I think it was important for Minesh to present because he's going to leave Zurich sometime soon, and perhaps this was his last, let's say, in-person lecture in classes, given that he's essentially done with his PhD defense. But I will maybe make a quick comment on this research as well as Minesh's dissertation research. These are actually quite important problems that perhaps more people should be tackling because these errors are going to get more and more in scale technology nodes, as we have been discussing, and as we've been seeing with RowHammer, for example. So looking into these ways of profiling errors at high error rates and mitigating uncorrectable errors, recovering from them, and continuing the operation in the presence of these even uncorrectable errors is going to be even more important into the future. And I think a lot of Minesh's work paves the way for doing so while also implementing on-die error correcting code mechanisms. So if people are interested in doing research in this area, I would recommend reading Minesh's papers as well as his dissertation, which outlines some future works in this area. And he also has recently delivered a Safari live seminar on this topic, which I have included the link of in the YouTube chat. If you're interested, we can also put it on the course website, actually. Okay, with that, I think if there are no more questions, we should finish the lectures. And thanks for people who have stayed for long. That's hopefully you stayed because of your interest and not because you didn't want to go out, because you're not required to stay, clearly. But hopefully this gave you a good overview of some of the research going on, and we will continue this with Ataberk's Quark TRNG work sometime into the future. With that, have a good weekend and take care. I'll see you next week.
Sorry, I had a logistical question about the course, if that's okay.
Okay, sure, go ahead.
Just real quick, like on the last week or after the final, we'll still have lectures, right? And then will that continue until like December 24th?
Mm-hmm. So the exam will be on December 17th. We have announced that, right? And technically, we don't have a lecture on December 24th, but we may have some research lectures on December 23rd for people's benefit.
Got it. Thank you.
Sure. Okay, any other questions? Okay, we're done then. Thanks, Minesh. And thanks everyone who have presented today, Hasan and Giray.
Thanks, Oner.
Take care.
Is this yours? No. Hey, it's us.